Hey everyone, in this video we will be fully reproducing the RoBERTa architecture. So in one of my previous videos we basically did a starter to RoBERTa, right? So we implemented a very simple version, kind of trained it on a very simple data set, but today we'll be looking at how do we scale this up and kind of train a bigger model on lots and lots of data. This implementation should feel very familiar to what we had already done in the previous video because, well, we already implemented it, right? We did the hard part, but there's going to be a couple of specific changes that we're going to be doing. The first change is in the masked language modeling strategy that we implemented last time, we did it sample by sample. So basically we provided the masking strategy on each sample independently. This time we're going to do them in batches. The logic, everything should feel very familiar. It should be, basically the same. We're just going to be doing it on batches of samples at a time rather than a single sample at a time. Other than that, we'll also be preparing a much larger data set. We'll be doing, I believe, the Wikipedia and the book corpus data set in this case, and then we will be training it in a distributed environment, so on multiple GPUs. Right, so let's go ahead and get started. The first thing we're going to do is actually prepare our data, right? So we're going to be leveraging the Huggingface dataset platform, that sort of stuff, and just make this dataset prep very simple for us. So let's go ahead and do it. So we're going to do from transformers. We're going to import our RoBERTa tokenizer fast, right? So we will just be using the RoBERTa tokenizer that has already been made for RoBERTa, makes our life simpler. Obviously, we could have also trained our own tokenizer on our own data set, but there's no need to. They've already done it for us, so we're not going to deal with that hassle. And like I mentioned, we're going to be using the datasets platform from Huggingface. So we're going to do import load dataset, concatenate datasets, because we have two different datasets that we're going to put together. And then we have our load from disk, right? And that'll be for us to verify later on. We can import time, but I don't think we actually use it. We're going to ignore that for now. And I actually used argparse for my implementation, so you can go on my GitHub, see how I did it there. I'm just going to avoid argparsing in this case because I don't want to type out all of those things. So let's go ahead and just type out the arguments as variables and go from there. So first of all, we're going to have a relatively large data set actually here. I've already prepared the data set, so I'm not going to run this script once we're done. I'm just going to show you the results because it takes about 20 minutes for it to actually, prepare, tokenize, and that sort of stuff. So let's just go ahead and start here. We're going to do test split percent. I kept 0.005% of this data set for validation. So there we go. We're going to use that. We then will have our context length. So this is completely up to you, but the original RoBERTa implementation has a context length of 512, so it can process up to 512 tokens at once. So we're going to make sure we do exactly the same thing here. We're going to keep it at 512. You could obviously do a longer context length, as most modern language models are doing, but the compute cost then obviously will go up with the transformer, so we're not going to do that today. We're going to leave it kind of the way the original implementation is. We will also do a couple extra things. So first we will do a path to data store. So when we're done, we're going to go ahead and actually save the data set, save the already tokenized data set. And I'm just going to use my kind of paths that I already have here. This is actually the path where I've already saved it. So again, I'm not going to run the script, but there we go. We also have our Huggingface cache. So if you're familiar with the Huggingface dataset system, everything you do on a dataset is actually cached. This cache directory can end up taking up a lot of disk space. So typically I like to have a separate directory where the caching happens rather than in the default directory that Huggingface uses. There's other ways you can actually change this. You can export a variable into your bash RC and change it manually there, but I just like doing it this way. So we're just going to do it that way. And let me just find the path. This is what I used, so that's what we're going to use again. So there's our cache directory. After we do that, then we will just have a couple other things. Seed, We're going to call it, I don't know, 42, whatever. So that's our splitting seed. Num workers, I'll do 32 because I can do that. And then HF model name, right? What's the name of the model we'll be using? And in this case, we'll be using the, what is it called? Facebook AI RoBERTa base. So there we go. That's the model we'll be using. And so this is actually the name of the tokenizer. We'll be writing our own model, but this is the tokenizer ID, the name of the tokenizer we'll be using. So let's go ahead and write our data prep. So we're going to create a function, prepare data, and we're just going to give it some arguments, which we actually don't have right now. So there's really nothing to pass here. We're just going to do that. And so the way we can do this is our tokenizer is going to be our RoBERTa tokenizer fast dot from pre-trained, and we can just pass it the HF model name. We can do if name equals main. Go ahead and just run prepared data, and we can take a look at what this tokenizer looks like. So this tokenizer will already have a lot of the stuff that we're going to need. Let me pull this over here, right? So we can do prepare data. This tokenizer will already have a lot of the stuff that we need. Let's make this a little bit more legible. It already has some of this added tokens, right? So our start of sentence token, pad token, end of sentence, unknown, mask. So all of these things are already in this tokenizer, which is why we're just using the pre-trained tokenizer, just simple for us. So there we go. We have our tokenizer. We need our dataset. So we will be, again, doing the wiki dataset, which we can do our load dataset. If you're running this for the first time, this will obviously download it, and I can't, let me copy this because I don't want to type this number out. So let's just paste this here. So I'll be doing the wiki dataset, which will be, the English partition of Wikipedia. There's multiple languages you can pick from, and then we'll be doing book corpus. So there we go. And for our cacher, we'll be doing the Huggingface cacher. So this will already go ahead, and because I already have the data set downloaded, we can actually take a look. It might just take a second to load the charts. And so we can see this is a data set with 6.5 million roughly samples, right? So there's 6.5 million rows of data in this data set. And what we see is there's ID, URL, title, and text. So let's just pick one at random. So let's look at the train. There's only a train split, and we can just pick maybe the 10th sample. It doesn't matter. So let's just take a quick look at what this data set looks like, and the other one looks basically identical. So we have here, ID doesn't matter to us. You have URL, so the path, where is the data. We have the title, like what is the name of this Wikipedia article, Academy Awards, and then we can see here we have all of this text all about the Academy Awards. Right, so it looks pretty good to me. There are a couple of little things. You can see like there's some new line characters, and there's going to be some tab characters, and just some random special characters all over the place. We're going to do a very simple cleanup of that stuff in just a bit, but for now, this should be pretty good, right? So here we go. We now have our text, and we similarly have this for both samples. So again, if you take a look, we have a column of text here, and we'll also have another column of text in the books data set equivalently. So we can take a look at that as well. Let's give this a second. It will have to load it. So again, this one has a column of text. This one has about, what is that? 1, 2, 3, 1, 2, 3. So this one actually has 74 million rows, right? So very, relatively large data sets that we're working with here. Again, it takes a second to download if you are running this for the first time, but there we go. What we want to do is just grab that column, specifically the text column, and concatenate them together. So we're going to do our wiki dataset is just going to be our wiki dataset dot very convenient functions, which is why we're using the Huggingface stuff. We can select a column, and we're going to be selecting the text column. And again, books dataset is going to be our books dataset. We're going to select a column, and again, the text column. And so our final dataset is just going to be concatenate datasets. It's a method built right in, and we want to concatenate together our wiki dataset, the train split of it. There's only one split, so that doesn't really matter. And then our books dataset, again, the train split. And so our final dataset, we haven't tokenized or done anything yet, but our final dataset will look kind of like this, right? So we have this many samples of text in our data. Right, so there's all of our data set ready to go. Again, if you're working on your own data set, then you probably will be building, it won't be exactly like this. This is just using some of the data that already exists in the Huggingface platform just to get us started a little bit quicker. And so now that we have our data set, we can go ahead and do dataset.train test split, right? We're going to go ahead and split our data with a test split, or actually it's called test size, I think. And we picked it, what did I call it? Test split percent, right? So that's what we're splitting by. And then a seed of our seed, just so we have the same split every time. And now if we look at our data set, this might take just a second to, oh, okay, I guess it's already cached, so it's fine. So there we go. We now have a train and test split of data. So we have about 402,000 samples selected for testing and about 80 million samples for training. So there we go. Good. The original RoBERTa implementation obviously used more. Like there was much more data actually that Facebook used, but I do not have the resources to fully actually reproduce this model because that would require an insane amount of compute. So we're trying to do a reasonable baby version of it just to get some evidence of, learning and training some of these bigger language models. Okay, so now we need to go ahead and actually clean up a little bit of this data and tokenize it, right? So we're going to do def compute tokens, and we're going to pass in examples. We're just going to create a function in a function. That's fine. We're going to use this function in just a bit. And examples is just going to be a list. So let's basically a list of samples, right? A list of samples. And so what we're going to do is sentences is going to be an empty list. And we're going to do for example in examples text, right? So there's going to be a examples text will be a list of our text from our data, and we're going to loop through them one sample at a time, right? So for every one of these samples, we're going to do sentences.append, and we're going to do dot join, right? Example dot replace. First, we're going to replace all of our new line characters with just an empty character, and we're also going to replace dot replace. Dot replace. Again, we're going to replace our tab characters with just an empty character, just so we get rid of them. And then we're going to do dot split, just like that. So this is just going to go ahead. This is going to go ahead and replace all our new line characters with nothing, replace all our tab characters with nothing, split it up by the spaces because there might be extra white spaces, and then just put it all back together with spaces, just so it's nice and clean and ready to go. And then we can return our tokenizer that we already defined above. And we're going to just pass in those sentences, right? Already cleaned sentences. And we're going to do return attention mask is false. We won't really need them here. We'll create them later. So we can actually try this. Tokenized data equals dataset dot map. And we're going to do the compute tokens function is what we want to apply to everything. We're going to do batched equals true, right? We want to do this in batches. Num proc is going to be the num workers that we defined above, and remove columns equals text, right? So once we're done tokenizing our data, we don't actually need the text column anymore. All we need is the tokens. So again, this will just be a very simple cleanup of our data. And we can print our tokenized data here, and let's see if this is cached or if it's going to run it again. I have a feeling it's going to run it again, and this is one of the steps that takes a couple of minutes. Yeah, so it looks like it's going to be running. So you can see it's running. It's effectively processing one sample at a time, kind of with this stuff. So I'm going to force an error real quick. Let's just do raise exception, right? So whatever. I just want to show you quickly a little bit what's going on internally. So print sentences, right? So we can take a look. If we take a look here, we'll see kind of exactly what I mentioned. Let's give this a second. It's going to run. It's going to print out 1,000. It's fine. It raised an exception. So you can see basically we it's the same text as before. We've just removed some of those new line characters, tab characters, that sort of stuff. So we don't really have any of that anymore. We could probably do more to clean this text, but it's fine. It should work perfectly fine for what we're going for. So we're good to go. So this is fine. And then once we've done this, right, we can, let's see, let's call this tokenized. Is that? Let's move you above, and we can print tokenized. There we go. Just so we can see what this tokenized text looks like. And it should be exactly what you think. Instead of just having the raw text, we're going to actually see our, tokens, the numbers that represent the different words. So here you go. So we have our tokens. You can see we always have a start token at the beginning. At the end of this, I'm sure there will be an end token somewhere. So either way, this is kind of what we're working with. These are the actual tokens that will be passed into our model later on. So we're good to go. We can now return tokenized, and we're good to go there. And what we're going to do now is, this is the part where I can't really run the stuff anymore, but you can imagine what's happening, so it should be fine. So we have basically all our text is now tokenized, and we're good to go. And once we have done that, now we need to group our text. So the idea here is that we have text of different lengths, right? Like, the first sample might have 1,000 tokens, and the second sample might have 300 tokens, and the third sample might have 400 tokens. So every sentence is of a different length, and there's two ways we can handle this. We can either A, just grab for things that are longer than 512, then we can just go ahead, because 512 is the context length that we selected. Anything that's longer than 512, we can just randomly select something that's 512 long. Anything that's shorter, we'll just add the pad tokens to it. But in practice, adding pad tokens is kind of a waste of compute. Like, the model will be processing the pad tokens, the transformer, but the pad tokens don't mean anything, and we effectively just ignore them when we do the attention masking, right, later on. So it's better just to chunk our data into 512 length tokens, so we don't really have any padding tokens. Everything is just of length 512. So we're going to take all our text and chunk it up into lengths of 512. It's as simple as that. So we're going to do def group texts batch, and what we're going to do here is concatenated texts. What we're going to do is, this is basically a list of tokens, or a list of tokens, effectively. So you'll have like a list, and inside this list you will have the first thing, which will have some tokens in it, the second thing, which will have some other some other tokens, and it may be of different lengths, or it may not be, so every sample is different. That's what this batch is, just a list of tokens. So we're going to go ahead and just create one long list of all of our tokens. We're just going to concatenate all of it together, and then take that concatenated list and chunk it up into lengths of 512. So to do that, very simply, we can do for sentence in batch, and we're going to call these were called input IDs. When they were tokenized, they'll be called input IDs by default, because that's how the Huggingface tokenizer works. So input IDs. For every sentence, we're just going to do concatenated text dot extend, right? Extend sentence, right? So we're going to go ahead, take all of our tokens, and just create one long sequence, so we end up with something kind of like this, right? So we're going to take everything and put it into one list, just like that. And now we're going to take this list, however long it is, and chunk it up into our context size that we want. So if our context length was 4, then we'll say, oh, I want these 4 tokens as the first sample, these 4 tokens as the second sample, these 4 tokens as the third sample, ... right? So we're going to just chunk it up, simple as that. So to chunk it, all we need to do is concatenated text is going to be equal to concatenated text I to I plus the context length that we selected. So we're going to go in the start, I will be 0, so it'll be from 0 to 512, and we're going to do it for I in range. It's going to go from 0 to len concatenated texts, right? So we're going to go from 0 to however many samples we have in increments of the context length, right? So it's going to go from 0 to however many tokens we have in chunks of 512. Now, when we do it this way, we're actually going to end up throwing away a little bit of data, because if your text isn't divisible by 512, right? Let's say you have 1028 tokens, right? In total, you have 1028 tokens in this. Well, the first thing's going to go from 0 to 512 or 511, and the second thing's going to go from 512 to 1024, but you still have those 4 extra tokens left over at the end, right? The 1028, and those just kind of get tossed, but in the grand scheme of things, it kind of works out fine. That we don't end up throwing away any significant amount of data. So there we go. And data is then going to be input IDs. And we're going to create our concatenated, need to stop doing that, concatenated texts, right? So we're just going to create, this is a input ID, it's going to be a list of lists of our text, and we return data, right? Just like that. And so now very simply, we can do tokenized data is going to be tokenized data.map, just like before. We're going to do group text as the function we want to do, batched equals true, and then num proc will be num workers, right? So how many workers we want to do this. So this will go ahead and chunk our text up into 512 length chunks. So every sample is exactly 512 tokens, making our life a little bit simpler when we actually go to train the model in the future. And finally, all we need to do is tokenize data dot save to disk. And we're going to save it in our path to data store, right? So wherever we want to save it, this will just create a full copy of this data and just go ahead and save it so we can access it, and we're good to go. Now, obviously, like I mentioned, running this takes about 15-20 minutes, depending on how many, well, basically how many workers you have available to you. I don't want to put you through that because I've already run it. So let's go ahead and just take a look at what the data looks like when we're done. So we can do data is equal to load from disk. And we just have to provide it the path that we already have here. So path to data store, I believe. So hopefully this works. Print data. And we can go ahead and run this, and we should see that this is our data, right? So this is our data. We have 1, 2, 3, 1, 2, 3, 1, 2. So we have about 10 million samples. We have about 10 million training samples and about 53,000 testing samples, each sample being of length 512. And we can, let's see if we can verify that. We can look at our training split, and let's just look at the first sample real quick. So there is our input IDs, right? So that's our data effectively, right? That's our data. So we can go ahead and look at the input IDs, and let's just take the look at the length of it. And we should see 512, right? So each of these samples are of length 512. So there's 512 tokens in here. This is why, because all of our samples are of length 512 now, we don't really need to worry as much about things like our padding token and stuff like that, because there's really nothing to pad. But there's one thing to keep in mind here. Notice how we have a sample. So this is 0 was our start of sentence and 2 was our end of sentence. So this is one sample right here. And then concatenated to it is another sample. And then concatenated to it is another sample, ... right? So we have all these samples that have been concatenated together. Now, when we compute attention, personally today we won't be doing any extra work here. But technically, when we do compute attention, we don't want tokens from one sample to attend to tokens of other samples. I don't know how much it matters in practice. I feel like the neural network will just end up learning that this is start of end sentence of end of sentence. So these samples don't really need to care about the other samples because they probably don't go together. Like one could be about astrophysics and the next one could be about trees or something, right? We don't know. It's just Wikipedia articles or book corpus articles. So that's just something to keep in mind. Technically, we could be doing a kind of a different type of attention mask where we only a sample can attend to itself, and then the sample would attend to itself. That'd probably be a little bit more efficient. But again, today we won't be doing anything too complicated because I don't think it matters, and the neural network just kind of learns these start of sentence and end of sentences, effectively just delimiters between samples. But either way, we'll kind of keep it like that. So that goes ahead, that ends our data preparation step. So now that we've prepared the data, it's time to write a data loader, right? Before we're going to train our model, we need a data loader. So I'm going to create here a file called utils.py. And in utils.py, we're going to start sticking all of the stuff that we need to train this model. So let's go ahead and pull this up. Here we go. So first of all, we're going to need import torch, import random. We're going to do from typing, import literal. We'll be using that a little bit later, so not just yet. We need from transformers, import RoBERTa tokenizer fast. Now we don't actually need the RoBERTa tokenizer fast because we've already tokenized our data, but we'll need it for a completely different reason, and you'll see that in a bit. Data classes, import data class, and as dict, and you'll see why we need that later on. So there we go. Now, what we're going to do is, let's just like before, if name equals main, and we're going to need from torch.utils.data import data loader, and we also need from datasets import load from disk. So like we already had earlier, we can go ahead and just copy this. We're going to need u, and our path to data store was u. So we're going to just go ahead and grab that. And again, right, this will just give us our data that has already been tokenized and ready to go. And with this data, right, with this data set, we want to produce our data loader. So we can do loader is a data loader on our data. Let's do the train split, and let's do a batch size as 4. Shuffle. We don't need to do any shuffling or anything right now. Let's just do that. I'm going to do 4 samples in loader, print samples break. So this should technically work, but it also technically is kind of weird. So as you can see, the way that it's doing its data collation is incorrect, right? So we need to actually write a data collator that will be better, right? So let's go ahead and write a collate function, right? That's step 1. So we're going to do def RoBERTa masked, what do I call it? LM, masked language model, collate function. Long name, but it's fine. And in here, we're going to be passing in the config. So let's go ahead and write our config. We don't really need the config here, but we are going to need it later, so we might as well go ahead and write it. So this config, if you're familiar with how Huggingface does their config files, which effectively defines the entire structure of the model, we're just going to make something very similar here. So class RoBERTa config, right? And we just need to define all the different things that is in our model. So first of all, we will have our tokenization config. So we're going to do vocab size, this is an integer, and the RoBERTa tokenizer has 50,265 possible tokens in its vocabulary. And then we have our start token is 0. The end token was 2. The pad token, which we don't really use, but we will just include it, is also 2. And then the mask token is 50,264. So they use the same, they use the end of sentence token, basically the end token, for both indicating that this is an end of sentence and as a pad token, which makes sense, right? Because pad tokens only happen after the end of sentence, so you just add more of these end of sentence tokens. We again won't care too much about the pad token because of the way we've structured our data, but that's fine. So these are our tokens. If you're confused, you can again just look at the tokenizer and it will spell it out for you there, right? It tells you exactly what is the index for each of these special tokens. Now that we have that, we can go ahead and define the remaining part of the model. And this is going to be a very standard transformer-based model, right? So we have a embedding dimension is going to be 768. And we have to provide it the data type because it's a data class. So int 768. we will have the how many transformer blocks do we want? We want num transformer blocks int. Oh, that should be underscore blocks int. We want 12 of them. Num attention heads. Again, we will have 12 attention heads in each of our transformer blocks. MLP ratio. So just like default, it'll be an expansion factor of 4. Layer norm EPS. This is our layer normalization tolerance. So just to make sure we don't have a divide by 0 error. I think 1e minus 6 is the default anyway, but we're just going to set it there. Hidden dropout probability is going to be 0.1. Our attention dropout probability is again going to be, and these will be floats, float. Again, 0.1, just a little bit of dropout for the pre-training task. Context length is going to be, like we already trained our data, prepared our data to be 512, so it's going to be 512. If you had a longer context length, well, this would be the place to change it, and you could update the data as well to kind of handle or have access to these longer context lengths. We're just going with default today. We have our masking prob. So if you remember, the default masking strategy for RoBERTa is we will have 15% of the tokens as candidates for masking, but then we'll be doing the 80-10-10 split, where 80% of the tokens will be actually masked, 10% of the tokens will be replaced with another random token, and then the remaining 10% of the tokens will be left alone. If you're kind of confused about that, we spent a ton of video and kind of that primer to RoBERTa, which again will be linked down below because that's just a prerequisite for this. Then we have our Huggingface config. We don't care about this as much right now, but again, we're using the Facebook AI RoBERTa base. We'll basically be putting in a little bit of extra effort for most of y'all who don't have the compute resources to actually, do a full pre-training of RoBERTa. We want to make sure that in the next video, when we do a fine-tuning task of kind of the different fine-tuning things you can do, like classification or extractive Q&A or anything like that, you can actually follow along, and you can follow along by just leveraging pre-train weights that Hugging Face already offers, because again, most people don't have access to just have a ton of compute to pre-train this model. So this will just make it a little bit easier. So in that situation, this is the model we'll be using as the backbone, and we'll write the logic for that later on. Now we're going to do pre-trained backbone, right? So this is the literal part. So literal just means has to be one of these options. Either we used a pre-trained backbone, this would be our pre-trained backbone when we go to use it, or we use pre-trained Hugging Face. So this would be the indicator that we want to use the Hugging Face pre-trained backbone. And just as a comparison, we're also going to do random, as we don't have any pre-trained backbone. It was a randomly initialized backbone. So there we go. And then we're going to do path to pre-trained weights is going to be none. Right? So for now, it's going to be none. Later, we'll have one. So there we go. So this stuff here is just to let us an indicator of what we want to use. If you're following along and don't have compute resources to do a full pre-training on your own, then obviously that would be a good opportunity for you to just use a pre-trained backbone, and then you can continue following along just so it's accessible to everyone. Last part, this is just a little thing we have to do. When we do the fine-tuning, I like doing the fine-tuning using the Hugging Face trainer. The only reason I like that is because that's what most people are doing. Now, the Hugging Face trainer already works with all of the Hugging Face models. Like that's obvious because it's it's built for that. But you can actually use the Hugging Face trainer with your own model, like I will be showing you later, basically in the next video when we do some kind of fine-tuning. For the pre-training task, we're going to write a actual pre-training script, do everything from scratch, so we won't be touching the trainer. But for fine-tuning, just to make life a little bit simpler, it'd be nice to be able to use some pre-built stuff just so you can see how you can leverage existing code for your own projects. Now this trainer expects the ability to convert this data class effectively to a dictionary with a function called toDict. I found that out through an error, so I'm sure it's there somewhere. But for now, we're just going to do that. Right? This is just going to take our RoBERTa config, convert it to a dictionary with all the same values, and just return it, right? So there you go. Nothing crazy. So this is the config we'll be using. We don't really care about most of this stuff just yet. This will be more applicable to the model later. But for now, we're going to keep it like that. Good. All right. So now we will write our collation function, and then we'll write the masked language, basically the masking strategy again. So let's go ahead and do that. So our tokenizer is going to be the RoBERTa tokenizer fast dot from pretrained config dot hf model name. Right. So this is the name of the model that we'll be using. So let's go ahead and create that. We're going to do our collate function. Let's do def collate function. And our collate function will take a batch, just like always. I'm going to throw a pass in here so we don't do anything. And we're going to return our collate function, right? So this is a function that will return our collate function once we've defined it. So this is how I like to do it. You could also, again, create a data class for the collate function, but you can do it however you want. I just like a function that will return our collate function once it's ready to go. That way I can pass in some additional arguments like the tokenizer and whatnot. So let's go ahead and do that. Our collate function is just going to be our RoBERTa, all that stuff. We also have our config is our RoBERTa config. We'll just leave all the defaults. And we can pass in our config right here. Right, so there we go. And so now in our loader, we can define our collate function as our collate function. And which means now we can go ahead and print out the batch here just to see what it looks like. We can get rid of u because we don't have anything to print out yet. And hopefully this works. Let's see. So this is a batch, right? So we have an input ID and it is a list. So here's our first set of input IDs, second set of input IDs, third set, right? So we have all these input IDs here. So let's go ahead and grab them. So first step is we just need to get everything. Input IDs is going to be torch.tensor. We're going to remember these are all lists, right? We want to make them tensors, so we're going to do that. So torch.tensor sample input IDs for sample in batch. Right? We're going to grab all of them. And so now we can do input IDs very simply. It should just be a list of tensors, just like that, right? So there's our sample number 1, sample number 2, sample number 3, ... So that's all our data, or this specific batch. Now that we have our batch of input IDs, it's time to go ahead and pad and concatenate the batch. Now, in this situation, we'll be creating this pad token and the mask, all that stuff, but it doesn't really matter because everything is already of length 512, but just in case you did it differently, this will just be a catch-all that'll handle an exception that doesn't exist. So input IDs is going to be torch.nn.utils.rnn.pad sequence, right? So simple function to pad your sequences. We're going to pass it our input IDs. The padding value is going to be, again, this is why we loaded the tokenizer up here. So we can just pass in some information like tokenizer dot pad token ID. I could have also used this, right? I could have also done it for my config, but that's fine, right? Tokenizer.pad token ID. These things are built in anyway, so we can do that. And we, just like always, we want batch first as true. So now when we look at our input IDs, we actually shouldn't see any padding. You can see there's no pad tokens being added because everything is already of length 512. All the sequences are of the same length, so this doesn't really matter, but there we go. So we have our input IDs there. Now it's time to create our attention mask, which again should just be ones everywhere, but that's fine. It's going to be torch.ones. It's going to be len sample for, let's see here, len sample for sample in input IDs, right? So again, this doesn't really matter. Actually, we should have done this before, right? So technically, if things are of different lengths, we should do this ahead of time, but that's fine. So first we'll create our attention mask on the original input IDs where everything is the same length anyway, but it doesn't really matter. If we look at our attention mask here, it should just be a bunch of ones, right? So it should be a bunch of ones. And all these ones are of length 512, but the one indicates that we do want to compute attention on these things. And then we're going to add zeros to the ones that we don't, but there shouldn't be any zeros here because everything is already of length 512. There is no pad tokens. So either way, we have that. To do that again, attention mask is going to be equal to torch.nn.utils.rnn.pad sequence. We're going to do it on our attention mask with a padding value of 0, and again batch first equals true, right? So again, this is a little unnecessary, but it's there. So now that we have it, now one thing we do need is the special tokens mask. So let's just quickly look at our input IDs. So our input IDs, although they are all of the same length, we do have special tokens like start of sentence, end of sentence, start of sentence, and other stuff, right? So we do have special tokens in each sample, or multiple special tokens in each sample. And the thing is that we don't necessarily need to compute. Actually, we don't want to mask out special tokens. Like when we do the masking strategy, randomly deleting a token so we can predict what those missing tokens are on the other end of the transformer, it wouldn't make sense to delete special tokens. Special tokens are basically delimiters. It's not really text, it's not information. So we're going to create a special tokens mask for now, and we're going to use that in the masking strategy in just a bit. So how do we create that? It's very simple. We can just do special tokens mask, right? It's just going to be torch.isIn, right? It's a very simple function that will check our input IDs, and we're going to make sure we're going to create torch.tensor of our tokenizer.allSpecial IDs, right? So all special IDs will just create a list of what are all the special IDs. It's basically these numbers here, 022 50,264. It's a list of those, create a tensor, and then this will just identify which of these tokens in the input IDs are one of these tokens, and we can check that. Print the special tokens mask, and you'll see that. Let's go ahead and print it out. We can see that this is a special token, so it's true. These two are special tokens, so these are true, right? So it identifies which tokens are special tokens. As simple as that. Again, we're going to need this in just a bit. So now that we have our data tokenized, padded, everything's ready to go, it's time to go ahead and identify or do our masking strategy. Now, do remember, if we had pad tokens here, if the sentences were of different lengths, if we had pad tokens here, these pad tokens would also be identified as true, as they're a special token. So we also would not be doing any kind of masking of these pad tokens. We don't have them, but if they were there, then those would also be true. Just an idea. So now let's go ahead and create a function that will do our random masking. So we're going to do random masking text, and this function will return two things: tokens and labels, right? So what are my tokens that have been masked, and then the corresponding labels, the things we want to predict. And we'll be writing this function, random masking text, in a bit. And it's going to take in our input IDs. It's going to take our special tokens mask. And then it will take all the other stuff we need. Vocab size is going to be tokenizer.vocab size. Our special IDs is going to be our tokenizer.allSpecial IDs. Right, so those are my special tokens. The mask ratio is just going to be our config.maskingProb, right? Because we do have our config here. It's a variable accessible in the inner function, so we can pass in the masking probability that we want. And then lastly, we will have our mask token, which is going to be tokenizer.maskTokenID, right? So let's start that. Oh, there we go. So that's all the stuff this function will take in. So let's go ahead and write that function. It's going to be def random masking text, and just like I had earlier, let's just copy this actually, just so I don't have to write it out. We have some defaults, right? What are the tokens? Special token mask, my vocab size. This is the list of my special IDs. So there you go. This is my masking ratio, and this is my mask token, right? The index of the mask token. So there we go. So now let's go ahead and write the masked language modeling strategy. Now, one thing to keep in mind here is this will look almost identical to what we had done earlier. It's just we will be doing it on a batch of samples rather than a single sample, right? Other than that, it'll be identical. So let's go ahead and do it exactly how we did before. So we first generated some noise, right? So we're going to do random masking is going to be torch.rand, which is uniform, and we're going to be passing in tokens.shape. So this will create uniform, it'll generate random numbers uniformly between 0 and 1, and then anything that is less than 15% or less than 0.15 will be a candidate for masking, right? Because we're selecting 15% of our tokens for masking. So let's go ahead and print this out just so we see what things look like. And let's just return none and none. Otherwise, it'll just keep throwing an error that I want two things here. So that's just a placeholder for now. So let's go ahead and run this and just make sure it works. So we have generated here some random numbers, right? Some random numbers. What are the things that have been selected for masking? But remember, we want to ensure that we never mask out a special token, right? So that's why we produce the special token mask. So we can then go to our random masking. We can index wherever our special token mask is 1, right? So 1 for true. And we'll just set these to 100%. So for example, I know, here's a good example. This was a special token, if you remember from earlier. This would currently be selected to be masked because it's less than 15%. We're going to make this 100%, so it will never be selected to be masked, because I will write the logic later where anything less than 0.15 is selected to be masked, right? Or a candidate for masking. So there we go. If we now look at our random masking, we can see that these are now all ones, right? So because it's greater than 0.15, it will never be selected to be masked. It's as simple as that. So now that we have our random masking ready to go, we're going to do random masking is going to be our random masking less than our mask ratio. And we should see at least a couple samples, but maybe not. Okay, it looks like this token was selected to be masked. Again, it's random, right? So let's maybe print out the first sample just so we can actually see something. So we can see these tokens have been selected as candidates for masking, right? As simple as that. So we're good to go here. And now what we're going to do is labels, right? What are our labels? By default, they're all -100 because cross entropy loss, when we go to do our loss function later, will ignore any label that's -100. And so that's good, right? So we're going to be ignoring that. So we're going to do torch.full. It'll be in the shape of our tokens.shape. And we're going to fill it with -100. Print labels, right? So we should just have a tensor full of -100s as stuff we don't want to compute attention or compute losses for. And then for the things that were selected to be masked, we will update the labels accordingly, right? Just like we did in the earlier example, we're just doing a batch of examples again. And what we can go ahead and do now is our labels at the places that have been selected for random masking, right? So wherever random masking is true. So these are the tokens that have been selected to be candidates for masking. All of these are the tokens that we want the labels for, right? The things that were selected to be masked are the things we want labels for, and everything else should be -100. So we're just going to be indexing our labels wherever random masking is true, right, by default. And we're going to switch, we're going to set these to tokens, again, random masking. So what we're doing is, remember, labels and tokens are of the same shape. Labels is just a bunch of -100s. The tokens is our data. And what I want to do is wherever tokens is selected to be masked, which is this. So wherever tokens is masked, so that wherever this is true, I want to set these tokens inside my labels. So now we can print out our labels. And just again, to see it, let's just look at the first example. So we'll see our labels. They're negative 100 everywhere, except for the tokens that were selected to be masked. And for those tokens that were selected to be masked, these are the correct answers. So the model needs to predict that this token is token number 12801, and this token is token number 10,010, ... right? So it needs to be able to predict that. Everything else is negative 100 because they were not selected to be masked, so the model should not be computing any kind of loss on those tokens. So there we go. This will go ahead and set our labels, and labels are now ready to go. Now that our labels are ready, we need to do the 80-10-10 strategy of 80% of the tokens will be selected to be actually masked. So we'll replace those tokens with our masked token, but the remaining 10% and 10%, or 50% of the remaining 20% that's left over, those tokens will be selected to be either left alone or replaced with a random token, right? Just like we did before. So how do we do that? We can do random. So this is actually kind of cool. We can do random selected index is going to be our random masking, or just random masking. And we're going to do non-zero. It's a really helpful function that does this, random masking. There's actually a couple ways you can do this. This is just the way I like to do it. It creates a, we need to do random selected index, not random masking. It produces a tensor like this. It produces a tensor. Notice that there's two columns and all these rows. This is basically the index in our random in our tokens that were selected to be masked. So for example, if we print our random masking, let's do that. I don't know if this is going to help, but we can see that row 0, column 1 was selected to be masked. Is that true? Well, here's row 0 and here's column 1. This was selected to be masked. So this is just an index, right? Basically the location, the XY location in the matrix of, or I guess YX, but you get the idea. The row column index of what things were selected to be masked. Similarly, we see this is true here. So we can see that the third column and 509th token was selected to be masked. So we know this goes to 0 to 511. So 511, 510, 509. So the 509th column in the 0, 1, 2, 3, the third row, was selected to be masked. So again, this is just an XY or row column index of the tokens that were selected to be masked. And we can do cool things with this actually in PyTorch. We can actually index our data using tensors. For example, I want all of the trues. I want where all the trues are. How can you do that? Well, how do you normally do indexing? I say I want the 0, so we know 0, 1. It won't be this in the next example because, well, it's random, but either way, let's just do it. We do 0, 1, right? So that's the 0th row, the first column. If we run that, this will give us the, whatever the value was there. In this case, it's false, right? It looks like 0, 4 was now selected to be randomly masked, but that's fine. What if I pass in our random selected index, and we're going to pass in first all of the first column. So that's going to be all the rows 0. And then we're going to pass in random selected index, all the rows, and the second column. So what I'm doing is I'm passing in a vector here of indexes and a vector here of indexes. And this will produce all of our trues. So let's take a look. This gives us all of the trues. Because I'm basically saying that I want, in this case, right, this one here is all of the zeros, ones, twos, this first column of indexes. And then this here is our second column of indexes. And so PyTorch will get a column, basically a list of indexes and another list of indexes, or a tensor of indexes and another tensor of indexes, and then automatically couple them together, pair corresponding indexes together, and return those together. And we'll be leveraging that, I think, in just a little bit, right? Just to make our life a little bit simpler for filling stuff in. So we'll see that be used in a bit. But for now, let's just keep going. What we're going to do is a masking flag, right? So we're going to do a masking flag. We want to select 80% of these selected indexes for masking, right? We'll replace them with that mask token. So let's go ahead and do that. So masking flag is going to be torch.rand, and it's going to be len random selected index, right? So print masking flag, and you will see that right here, right? So for every sample that was selected, or for every token that was selected to be masked, I've generated a noise vector here. And then anything that's under 80%, because I want 80% of these things to be actually replaced with mask tokens, anything less than 80% will then be replaced with the mask token. So let's do that. We can do our masking flag is our masking flag less than 0.8, right? 80, we're doing the simple 80-10-10 split, so masking flag. There we go. We have our masking flag. And so very simply, selected index for masking is random selected index, and we'll grab it by the masking flag, right? So what we're doing is we're grabbing, remember, the random selected index is which samples, the index, the row column index of the samples that were selected for masking. And then I'm just going to go ahead and index out all of the ones that were true. So if you print out random selected index and then print out our selected index for masking, what you should see is these are the row column indexes of all the samples in our data that were selected for masking, right? So that's all of them. And then the second one here is all of the ones, basically 80% of them, right? We've randomly sampled 80% of these indexes down here. So that's 80% of them. And so this is our row column index of all the tokens that we actually want to replace with our mask token. So now we can go ahead and do that. But one thing we need to make sure we do is unselected index for masking. Remember, this is 80% of the data. So now we need to make sure we just store the other 20% so we can split it in half, right? The other 10%. So we're just going to do, again, similarly random selected index, and we're going to just do a Boolean flip on our masking flag. So there we go. So these are everything that was selected to be replaced with the mask token, and we'll deal with this a little bit later. So we're good to go there. Good. So now that we have that, it is time to, we'll actually fill in the mask tokens in a bit, but let's just keep going. We now need to take this here, which is 20%, the remaining 20%, and split it into 10%, 10%, which is basically we want to keep 50% of the remaining 20%, so that's our 10%. We want to keep 50% of them, switch them to some random token, and then the last 50% and the last 10 remaining percent, we will just leave alone, right? So this is the exact same masking strategy we did earlier. So just like before, we're going to do masking flag is going to be torch.rand. All this code will actually look identical to what we had just done, but it's going to be len on just the remaining unselected indexes for masking. So what was still left over that has not been selected to be replaced with a mask token. So there we go. And we're going to do masking flag is going to be our masking flag less than, we're doing 0.5 here because 0.5 of our 20% will be the last 10% that we need. And just like before, we're going to do selected index for random filling, right? So we're going to swap these in with random tokens, will be our unselected index for masking, and we want it with the masking flag. And then similarly, we're going to do selected index to be left alone, right? So the last 10% that's left over, we're not going to do anything with them. We're not going to switch it to a mask token. We're not going to switch it with a random token. We're just going to leave them alone. And so this will be, again, our unselected index for masking with a Boolean flip on our masking flag. And so now it's time to actually update our tokens. So we're first going to do if, these are sanity checks, like what if for some reason nothing was selected, even though it's 80%, but it's random, so it could happen. If len selected index for masking, right? So these are the row column indexes of what we want to to swap with masked tokens if this is greater than 0. Then we're going to do our tokens. And this is where I mentioned before, we're going to be selected index for masking. We're going to do the first column as our row indexes, and then selected index for masking. We're going to do the second column as our column indexes, and we're going to swap these to mask tokens. Mask token. And let's see what that looks like now. Print tokens, and let's print out the first sample, and let's also print selected index for masking, just so we can take a look and see what this looks like. So here we go. So we can see so we're only printing out the first sample, so let's just look at the first one. We can see the 12th and the 14th token were selected for masking, right? So we're actually going to swap them with mask tokens. So let's take a look. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12th. So the 12th token was swapped with our mask token, 50,264, which indeed is our mask token. And then 13, here's the 14th token. The 14th token was also swapped with the mask token. Everything else was left alone, right? All the other tokens are the same as before, but only these tokens were changed to a mask token. So the transformer, again, needs to predict what is this token given all the tokens around it, right? But we see these mask tokens kind of, all over the place because we swapped about 80% or 15% of the tokens with these mask tokens. So there we go. So that's the first part, right? This is me changing tokens in my data to these mask tokens so the neural network doesn't know what's there, and it needs to predict what's there using the context around it. So there we go. Now we need to change these tokens here. So we pick the next 10% or 50% of the remaining 20%. The next 10% of our tokens needs to be swapped to some random token, whatever it may be. So let's go ahead and do that. So we're going to do if len selected index for masking is greater than 0, right? So, selected index for random filling, not masking. So there we go. If it's greater than 0, our non-special IDs is going to be list, set, range, vocab size, minus set, special IDs. So all we're doing, and actually we should probably make this ahead of time rather than making it over and over again. So I'm just gonna put that here. Yeah, that's fine. We could have also made a global variable above, but whatever, it's fine. So what we're doing here is all of the possible tokens. So if there's a total vocab size of 50,264, then there you go. That's my 50,264 tokens. And all we're doing now is changing our, and let's actually double check here. Yeah, we should be fine. So all we're doing is now changing our, or creating a list of all the non-special tokens, because when we're randomly sampling tokens, right, from our things to replace, we don't want to change it to a special token. That doesn't make sense. We want to change it to an actual token. So we're just creating a list of all the non-special tokens effectively. And again, we did this in the easy example earlier. There's one thing I do want to check real quick, just in case I made a small mistake, which is always possible. I just want to print out the tokenizer here. Print tokenizer, just to make sure I'm not making a dumb mistake. So here's our tokenizer. This is here. Actually, our vocab size is 50,265, not 264. Because it goes to 264. So so this is 265. I just made a mistake right here. So there we go. Either way, we were passing it in, but regardless. So basically we're going from 0 to 50,264 as our 50,265 possible tokens, but we're making sure our list of special tokens do not, or our list of real tokens do not include these handful of special tokens. Because when we're randomly selecting and swapping things in, that doesn't really make sense to swap in with a special token. So there we go. So this is our list of our non-special tokens up here. We can print out our, you get the idea, it's just a list, right? It's just a list of all the numbers from 0 to 50,264 that don't include these numbers here. So nothing crazy. And all we need to do now is randomly selected tokens is going to be torch.tensor, right? Torch.tensor. And we're going to do random.sample. We're going to randomly sample from our non-special IDs. We're going to random sample the len of our selected index for random filling. So basically we have all these numbers here, all these possible non-special tokens, and however many things have been selected for random filling, we're going to randomly sample that much stuff from here. And it's as simple as that. We're just going to randomly sample. And just like before, we're going to do tokens. And now we're going to do our selected index for random filling, the first column, and then selected index for random filling, the second column. And we're going to set this equal to our randomly selected tokens. As simple as that. So all we're doing is in our tokens, the indexes, the row column indexes that were selected to be randomly filled, we're going to sample that much stuff, or however many were selected. We're going to sample that many random tokens from our list of non-special tokens, and then just fill them in. And that'll do it. So again, this is the simple 80-10-10 split that we already explored earlier, just applied on batches rather than a single sample. But that's basically it. That is our process. These tokens here were selected to be left alone. So we don't need to do anything here, right? We don't care. Our labels are already updated, right? So for all three cases, whether or not we have a masked token, whether or not there's a random token, or whether or not nothing has been changed, our labels are already selected. So the neural network needs to be able to either fill in the blank when there's a masked token. It needs to be able to tell when a token is not supposed to be there, like, hey, this token doesn't belong here. And it also needs to be able to tell that, hey, this token does belong here, right? That's these kind of additional tasks that makes this a little bit more of a challenging pre-training task than just only having masked tokens. So there we go. That is effectively our masking strategy applied on batches rather than just single samples. But again, if you saw that earlier primer video, then none of this should have felt all that different, except for this kind of additional thing. Now, would you do all of this effort? Actually, let's finish this up, and then I'll show you the easier way of doing all this stuff if you are actually doing it, but it's good to be able to do this once yourself. So return tokens and labels, and we are good to go. So now we have here, print our tokens, print our labels, and we should see all the stuff we did worked out. So we can see that here, this token, 50 is a masked token, 50,264. So the neural network needs to use the context around it to predict what is this word. And well, here's the correct answer. That was the correct word at that spot. So this is effectively our masking strategy, what it's doing. And there'll also be the other cases as well, but I just don't see any here, so that's fine. Now that we have all of this ready to go, all we need to do is return our data. So we're going to do return. Our input IDs is going to be our input IDs. Our, let's see, we call them attention mask, is going to be the attention mask. And then finally, we have our labels, is going to be our labels. So we're just creating a dictionary of data, and that's what we're returning. And we are good to go here, which means when we print samples here now and break, we can go ahead and see that this is our data. Let's go ahead and get rid of this print. No need for this anymore. That was just a verification. But we have our data. We have our input IDs, our data. We have its corresponding attention mask. Notice everything is 1. Everything was of length 512, so there is no pad token. So there's really nothing for us to ignore in the attention mask. And here are our labels, right? The things we're trying to predict. And so again, in this case, this token was selected to be masked. Here's the correct answer, and it has to use all of the surrounding context to predict it, what it was. And all the negative 100s will be ignored by default. So it's as simple as that. So this is the full masking strategy set up. Now, just as a curiosity, from TQDM, import TQDM, we can throw a TQDM on here. Anytime you create a data loader, it's good to just quickly benchmark it, right? Just so you have an idea of is there any bottlenecks happening in everything that you just made? So we can make the num workers. Let's just make it 32 because I can do that. And let's just throw a pass in here for now. And this will just give you a quick estimate of ignoring the model. This data loader takes about, well, it looks like about 27, 28 minutes to iterate through a full epoch, right? So this would be one full epoch through the data. Obviously, the epoch will take much longer because we'll be training, we actually have to pass it through the model. That's the expensive part, not really iterating, but this just gives you an idea if there's some bottleneck happening inside your data loader. It's also why I love the Huggingface dataset stuff, because it's they're effectively just Parquet or PyArrow files, and it just goes really, really quick. So we are good to go here. Now, as a quick caveat, let me pull this up real quick. Data collator for masked for language modeling is, I believe, what they call it. So in Huggingface, like if you don't want to write all this code, though a lot of this code actually was inspired by their code, so this is just a good reference. They have a data collator for language modeling right here, where you can provide it. Are you doing masked language modeling? Are you doing an MLM? What's the masked language thing? Probability. We can take a look at this source code as well. And you'll see a very, very similar structure. So you'll see here, hey, we're doing replacing indexes, and we're just randomly grabbing stuff, and yada, 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 right? So very, very similar code. I think that was the TensorFlow code. I can't remember. Either way. So very, very similar code. Just we did it ourselves, right? But you could, obviously, if you don't want to, you could have used this data collator as well. It's just good to be able to see all of this yourself, right? How to implement all this yourself. So we have now completed everything we need, I think, regarding the data part. We will be adding more to this utils file later in the next video when we write a similar processor, effectively basically a collate function and that sort of stuff, for the extractive Q&A model. But we are not going to be doing that today, right? Today we're just focusing on the pre-training task. So now that we have all of this stuff ready to go, we have our data. All we need to do is write the model and then write the pre-training script, right? So let's go ahead and construct our entire model. Again, we'll be just focusing on pre-training today. We'll be adding more to this file in the next video. So model.py, right? Very simple. And let's go ahead and do import os, import torch, import torch.nn as nn, import torch.nn.functional as f, and then from safe tensors.torch import load file. We won't be using that today, but we'll be using it later. And then we're going to also do from transformers import the RoBERTa model, so their RoBERTa model as HF RoBERTa model. Again, we won't be using this today. This is just if you don't have the compute to actually pre-train your own model, you can do the next video just starting from their model, right? Starting from a pre-trained backbone. We won't be doing, I don't think we'll be implementing that today. We'll see that next time. So let's go ahead and write all the pieces we need. What I'm about to write should feel very familiar because we have effectively implemented a simple version of this in the previous video. So let's do a quick recap on what we had implemented last time. So here we go. Let's see here. Where do we start the model? So again, this is the masking strategy we wrote last time, but notice that we wrote the masking strategy straight inside the dataset. So this is a per sample masking strategy. This would have worked just fine as well. Like this would have worked just fine in everything we had done. I only moved it to do it in batches at a time. So within the collate function, for the sole purpose of making it more similar to the Huggingface stuff, just so when you're looking at their code, if you have some ideas that you want to, change around, you already understand the code. But either way, as you can see, basically the same thing. We didn't really do much different. It's just in our indexing, we only had one sample, so we only had one column in our thing, but we had two in our case, so we had to, the row and the column vectors, but either way, it's fine. That's our collate function. We're going to ignore that. Okay, So we have to implement attention. So it should look very similar to this. So we'll get there. I have a feeling. Yes. So in this implementation, we just wrote our own attention mechanism because it's fine, right? I wanted to show you how this works just to give you a little bit of a recap. How do you do the attention mask, stuff like that. If you want more detailed explanation of attention, I will link the video above right now to my kind of like super in-depth video on literally anything and everything you would need to know about attention. So you can reference that if you're a little bit lost. Today, when we implement it, we'll be leveraging flash attention, right? Like why not use, if we're training a big bad model, I want to get as much performance out of my GPUs as possible. So we'll be using flash attention there. So we have our attention, so we'll have to implement that. We'll have a multi-layer perceptron, we'll have a transformer block, we have a RoBERTa. We'll also have our CLS token, our positional embedding. So all very similar. Now I'm going to structure how we implement this, again, just very close to the Huggingface implementation. They like to modularize literally everything into different parts. It's actually very convenient for the purposes of like changing small things in the code. So we're going to do exactly like that, right? Nothing too crazy, nothing too different. And once we're done with that, we'll go ahead and write the training script and we'll be good to go, right? We'll be done. So let's start with our embeddings, right? So we're going to do class RoBERTa embeddings. We can do all sorts of different types of embeddings here. We can do sine cosine, we can do learnable, we can do rope embeddings, we can do alibi. It doesn't matter. There's all sorts of options, but they use learnable embeddings, so we're going to use learnable embeddings. So just like every model, def init self, and I'll be passing in the config for everything. So this makes our life simple because inside our config, we already have all the information. What is the embedding dimension? What is, everything we need. Everything we need is already inside our config, so we can just leverage that. So we're going to be passing in the config for everything. And just like always, we need to do super RoBERTa embedding self.init, right? So step one, we need our word embeddings. So self.word embeddings. This is going to be nn.embedding. And this is going to be an embedding of our by config.vocab size, right? So how many possible tokens can I pick from? By our config.embedding dimension, right? So our vocab size, our embedding dimension, and then padding index is just going to be equal to config.pad token. Because again, remember the pad token, we don't really care about it. It's just a filler. We don't even need to compute gradients on it. So the embedding just gives you this option to just like include it. We could also not include it, but it's fine. We're trying to keep it as similar as possible. So there we go. That is our embedding matrix for our words. We also need our positional embeddings, right? Again, if you remember, transformers are permutation and variant. They don't actually care about the sequence of words, which means we need to inject some type of positional information into the model. There's all sorts of options that you can pick from today. We're just going with simple learnable embedding. So self.position embeddings is going to be nn. Embedding. We could have also done a parameter. If you remember, we did nn. We did actually positional embeddings here. So we're going to keep it like that. Okay. So we're going to be doing a nn.embedding, config.contextLength, what's the maximum context length we can process, and config.embedding dimension. You could also include context length +1 here, if you remember. Reason we did this is because we also had that CLS token that we added on. You can do that separately. When you write like a RoBERTa for classification, we don't have to include it in here. We won't be doing a classification fine-tuning test because I think it's too simple, and there's plenty of YouTube videos or examples that you can find for that. That's why we'll be doing the more complicated extractive Q&A, but it's fine. We're just going to be keeping it to this right now and just keep it simple. Then we have self.layerNorm. All right, is nn.layer normalization, config.embedding dimension, right? So what's the embedding dimension you expect? And EPS will be config.layer norm EPS. This just makes sure we don't have a divide by 0 error, right? So we have our layer norm EPS. I think the default layer norm EPS that PyTorch already uses is already 1e - 6. So It doesn't matter, but either way, we're just including it. And then lastly, self.dropout is nn.dropout config.hidden dropout p, right? So our dropout probability. And so now forward self, and here we're going to be passing in input IDs, right? The tokens, the numbers, all the data that we've done, because this is where we will actually be producing our basically our word embeddings, right? We're going to take our tokens, pass them through the embedding matrix to produce our word embeddings. So let's go ahead and do that. We have x is self, or actually let's go ahead and store ahead of time. Batch size by sequence length is going to be input IDs.shape, right? That's the data that's going to come in. And then we're going to do x is self.word embeddings. We're going to pass in our input IDs. This is going to go ahead and actually convert our tokens to embeddings. And then we need to add our positional information. So avail index. So how many tokens do I have here? It's going to be torch.arange from 0 to sequence length, right? So in our case, when we pre-train, all of our sequence lengths will always be 512. So we'll be leveraging the entire positional embedding. But during inference time, that may not be the case, right? So what we're going to do is grab indexes from 0 to sequence length, whatever the maximum sequence length is here, whatever it is. And then we're going to do dtype. We have to make sure it is a torch.long because the embedding matrix expects long tensors. And then our device is just going to be the same device where everything else is, right? So input id.device. And so our positional embedding is just going to be our self.position embeddings with the avail index, right? So if you remember, this is basically a matrix with 512 rows and 768 columns. And each one of those rows identifies the position embedding for that specific time step. So if I have only 10 time steps, then I want to grab indexes from 0 to 9 from my position embedding. So that's basically what's happening here, right? Nothing crazy. Let's see if we can make an example. If name equals main. And we can actually just grab, let's see. Actually, let's just do it ourselves. We're gonna do rand is torch.rand int, and we want to, let's say 0 to 1,000. We know we can go up to 50,000 something, but for now it's fine. And let's say the size is going to be a batch size of 4, and each sample is of length 512. Right, this is kind of what our data will look like, right? So Python model.py. Let's see if this works. RoBERTa model. Right, so this is kind of what our data will look like. It's just random tokens right now, but that's fine. And what I want to do is just pass it into our thing, just so we can see the what this all looks like. So we can do re and pass in rand. And so we can first print x.shape. So you know our data is 4 by 512. Now it should be 4 by 512 by, right? So we need to actually pass in our config as well. We don't need the config here. We'll need that later. So we can do from utils import RoBERTa config. And we can do config is our RoBERTa config. And here we'll just pass in the config so it knows everything about the structure of the model. Let's see if that works. There we go. So we go from 4 by 512 to 4 by 512, and each of those tokens are represented by a vector of length 768. So standard embedding matrix stuff, right? After that, we know there's 512 tokens, so we can do print avail index. This will just go from 0 to 512, or 511, right? 0 to 511, because those are the tokens that we had. If for some reason our max sequence length was like 25, then this would go from 0 to 24, right? Those are my tokens. Once I have that, I will just grab those corresponding tokens from my position embedding matrix, right? So we can do print position embedding, right? And this will just produce my vectors, right? This is my embedding for the first position, embedding for the second position. And there will be 24 of them because I have 24 positions or time steps in this data set or in this specific batch. So there we go. And all we need to do now is if we print pause embed.shape, print the actually now it's x.shape, right? We can see we have 512 by 768, so that's my position embedding. And in this case, it's basically the entire position embedding because I'm using all 512 tokens. And my data is 4 by 512 by 768. Again, if I change this to 25, then we would only be using the first 25 positional embeddings, and our data only goes up to 25, right? So there we go. And all I need to do is add this to this, and that's as simple as just doing x equals x plus pause embed. So this is me injecting positional information into my data. Then we can do self.layerNorm x is self.dropout x, and we can return x, and it's as simple as that, right? So I'm adding my positional information here. I could have also done an unsqueeze here. Technically, that would have been the better, more correct way of doing it. Unsqueeze 0. That would have added an extra 1 dimension here, so 1 by 25 by 768, and then it's a simple addition, but PyTorch will automatically broadcast this for you, so it's not really a concern for us. So there we go. That is our positional embeddings, right? Positional and word embeddings, right? So all the embeddings that we have. Now that we have our embeddings done, it is time to write our, I don't know, let's do attention next. Why not? So we can do class RoBERTa attention. Again, I'm going to speed run through this attention implementation a little bit because I have a whole video about everything you would need to know about attention. So I'm not gonna get into the nitty-gritty details, and we'll be using Flash attention, right? So it's not like we really need to implement attention in all that much detail here. So we're gonna go with it. We're going to do super RoBERTa attention self dot init. There we go. I'm gonna go ahead and store the config in here because we'll need that information. We'll need some of that information later, like how many heads do we have, that sort of stuff. So I'll just store the config here so I can access it in the forward function as well. So there we go. And we just need to do a quick check, right? We don't have to, but it's good to do this. Our embedding dimension divided by the config.num attention heads is 0, right? We want to make sure that our embedding dimension is actually divisible by the number of attention heads, which it is. We pick 768 as our embedding dimension. We pick 12 as this, so we have 64. Our embedding dimension per head is 64, so it's divisible. But if it wasn't divisible, then this wouldn't work. Attention wouldn't work out, and so we just need to do a quick sanity check here. Double check embed dim divisible by attention heads, right? Just like that. Okay. Open that. Okay, good. So we just need to do our sanity check there. Now that we have that, we can go ahead and do the rest of our stuff. So self.headDim, right, is just going to be our config.embedding dimension integer division by config.num attention heads, just like that. And we just need to define our 4 linear layers that we have in effectively every single attention mechanism, our QKV projections, and then our output projection, right? So we're going to do self.qproj is just going to be nn.linear, and it's going to go from config.embedding dimension to, again, config.embedding dimension, because we will handle the multi-head attention via just some tensor manipulation, right? Rather than doing anything extra. So we're going to have this. We're going to have our Qs. We're going to have our Ks. We're going to have our Vs, and then we'll have our output projection, which we'll see later. So standard attention setup, right? QKV and output. Okay. Now we need to define our forward function, x, and attention mask is none by default, right? So there we go. Very simple. We're going to be passing in our data, passing in an attention mask if we have it. But yeah, there we go. Now to do this, our random, we're going to do torch.rand, whatever, and we can make this shape 4 by 512 by 768, right? So that is our data, typical shape for things, for our transform models, batch by sequence by the embedding dimension. And what we want here is the RoBERTa attention, call this A, right? Doesn't matter, but there you go, A. And what we're gonna do is print x.shape, and we're just gonna ignore the attention mask because it's fine, right? The flash attention will do the attention masking stuff for us anyway, and in our case, when we pre-train, our attention mask is gonna be 1 everywhere, so it's fine. So either way, we have our data, and so just like before, we're going to do Q, or actually let's do batch by sequence len by embed dim. It's gonna be x.shape, right? So there we go. And so Q is gonna be self.q proj x. And then if you remember, right, if we print q.shape, and we'll walk through the shape again, this is going to produce a batch by sequence, but we didn't change anything, right? It's still 768. But this q here is a projection of the original x, right? It's a projection of our data, you know, to create the queries. What we want to do is multi-head attention, not just single head. So we need to take the 768 and split it into number of heads by the embedding dimension. So let's go ahead and do that. We can do dot reshape, oops. And batch and sequence len stay the same, right? Still batch by sequence len, but we're going to split the 768 into 12 heads by 64 embedding dim per head. So it's going to be self.config.num attention heads, which is why we created self.config here, just so we can access the config, right? How many heads do we want? And then self.headDim. And so now if we look at q.shape, we went from 768 and let's see here, config, fi. There we go. So now that we've split our 768 into 12 by 64, right? So that's me splitting my heads up. And now I can do my, remember, we want to do attention on, we want to parallelize across the heads, but do attention on the sequence by embedding dim, right? So this is my basically we have 12 heads, and each head has a sequence length of 512, and each token in this 512 is represented by 64, a vector of length 64, right? That's my typical setup for multi-head attention. So we just want to flip these two dimensions so we can parallelize across the 12 heads, right? So what we're going to do is a dot transpose 1, 2. That will go ahead and flip these two dimensions. So see, we went from 512 to 12 to, you know, we swapped them around. And so now we have 4 samples. Each sample is represented by 12 heads of attention. Each head is processing 512 tokens, and each token is represented by a vector of length 64. So it's simple as that, right? Now that we have that, we will repeat this 3 more times to create our Q, our K, and our V with the K proj and the V proj, right? And it'll basically create 3 different tensors, right? 3 different tensors in this shape, right? In exactly this shape. And this is all flash attention needs to work. Again, if you have some confusion over why we're doing all of this manipulation and that sort of stuff, and why are we doing multi-head attention, and what are the benefits, and you know, that sort of stuff, take a look at my attention video. We go into a ton of depth there and exactly why all of this is happening. But for today, we're going to just kind of assume a little bit of that as known knowledge. But yeah, just go back and review. It's not very complicated. You just have to, you know, take a look at it. So dot scaled dot product attention. So this is our flash attention. We could have also used flash attention, the package from Dell Labs, but this just avoids any additional installs. We can just use PyTorch directly. This will take Q, K, V, and we'll give it the attention mask, will be the attention mask if it's passed in. And then our dropout P will just be self.config.attention dropout P if self.training, else 0.0, right? Because if we are in, if you remember, self.training is a variable that's in every single PyTorch, like it's inside the nn.module. It tells the model, when we do model.train or model.eval, this is what we're toggling. So if we're in training mode, we want to make sure we are using the dropout that we indicated. And if we're in evaluation mode, we don't want to drop out, so we just set it to 0. So there we go. That's attention. And so now we can print attention out.shape. Here we go. And that's our final result, right? That's our attention result. Again, the output of attention is exactly the same shape as the input. This kind of makes it a little bit convenient, but we have everything we need here. All we need to do is put the 12 and 64 back together, which means we need to transpose these 2 dimensions and then flatten, right? Just put it back how we found it. So we're going to finally do a attention out is going to be attention out dot transpose. We're going to flip these 2 dimensions, 1, 2. And we're going to do flatten after the second dimension. And you should see we have our final result. Everything is just put back together. But again, remember, all of this computation that we just did, all of these computations, the head was parallelized on, right? So we computed multiple heads of attention, but the different heads have not had a chance to get to know each other. So that's why we have this final output projection to kind of just tie it all together. Attention out is going to be self.out proj attention out. And we can finally return attention out, and we are done, right? That goes ahead and finishes up our attention implementation. Simple as that. Again, this attention implementation looks so simple because we used flash attention. Otherwise, I mean, nothing would really change all that much. We would just have some additional, just a little bit extra effort here to actually do the QK transpose, do the masked fill, softmask. We'd have an extra couple lines of code here. It doesn't change anything in any meaningful way, so we're not going to worry about it. We want to use flash attention because we are going to be pre-training a big model, and it takes long enough already, so you might as well try to get the most out of the resources you have available to you to train these types of models. So that is our RoBERTa attention. Now that we've done RoBERTa attention, we are in the home stretch, right? Now's the easy part. We need to write our feed forward, a very simple multi-layer perceptron. We need to kind of put it all together into a encoder layer, define the encoder to our transformer, which is basically going to be our model, and then just define the final model, right? Everything that we want. So let's go ahead and do that. We're going to do first class, our RoBERTa feed forward nn.module, and this is going to be very simply def init, again, self config, and we're going to do super, and we'll have a RoBERTa feed forward self.init, right? Very simple. And this feed forward layer is going to be very, very simple. Our hidden size, if you remember, so our embedding dim is 768. Right? 768 is what we set. The hidden size will be the MLP ratio times 768. So it's going to be 4 times 768. So we're going to do config.embedding dimension times config.mlp ratio. And if you don't know, the feed forward layers is actually where a lot of those parameters are. A lot of basically the parameters of our neural network. So either way, we have them here. MLP ratio. That'll just dictate the middle layer's hidden size. And so we're going to call the self.intermediate dense. I only call this just to make it closer to the Huggingface implementation. So the code is, again, familiar if you ever have to actually change something. Embedding dimension. And we're going to go up to our hidden size. Right? Simple as that. And then we'll have an activation function. Self.activation is nn.GLU, right? Because they use the GLU activation function in these transformers. Self.intermediate dropout is going to be nn.dropout with config.hidden dropout p, right? So that's our hidden dropout probability. Then we have self.output dense. It's going to be nn.linear. We are again going to go from hidden size back down to config.embedding dimension. Right, we're going to go back down, and then again, self.output dropout is going to be nn.dropout config.hidden drop out p. Simple as that. So now we can go ahead and do def forward self x, and we're going to do x's. We're just going to pass it through all these layers, right? So self dot intermediate dense x, x is self dot activation, x is self dot intermediate dropout x, and then we're going to have our x is self dot output dense x, and then our final dropout x is self dot output dropout x. Return x. So very simple feed forward, right? Just two linear layers with some dropouts and an activation function, right? Should feel very familiar. Nothing new. Again, just referring back to code that you hopefully have already seen. Here you go, right? We have some activation functions. By default, we're using GLU. We have a dropout after every linear layer, right? Nothing new, nothing different. Now we have to write our block, right? It's just going to be a transformer block that puts the attention and the MLP together, right? So let's go ahead and do that. We can do def RoBERTa encoder layer and then dot module, right? So it's going to be a single encoder, and then the encoder will be a stack of these on top of each other, right? So again, we need to do def init. Oh, sorry. Class. My bad. Def init. Self. We're going to pass in the config again. Super RoBERTa encoder layer self dot init. And all we need to do now is just stick everything together. So self.attention is going to be our RoBERTa attention with the config, right? This is why I like the config files. Otherwise, I just have all this extra stuff, right, that I have to do. It just keeps us nice and clean. So we're going to do it that way. We'll have a dropout layer after our attention. So nn.dropout. And this is going to be config.hidden dropout p. And then we'll have our self.layer normalization. So we're going to have a layer norm. Again, it's going to be nn.layer norm. We need to pass it the config, the embedding dimension, dot embedding dimension. And then we'll have EPS is config dot layer norm EPS, right? So whatever the EPS is, it's fine. We then will have a feed forward layer, right? So self dot feed forward, and this is going to be our RoBERTa feed forward layer config. And then finally, we'll have another one of these layer normalizations, right? So after the feed forward, and this will be config layer norm. I'll call this final layer norm. Because again, if you remember the transformer architecture, each block is attention, then you do an add-in norm, and then you do feed forward, and then an add-in norm. So here's the norms. We still haven't done the add part yet. That'll happen in the forward, right? So there we go. So now we do def forward self x, and again, attention mask is none by default because we'll have to pass that in if it's there. And so let's go ahead and do it. X is equal to self dot attention x. Attention mask is attention mask, right? So that's what we're passing in. And then on this attention, right, once we've computed attention, we want to apply a dropout to it. Self.dropout. So there we go. This will add a dropout layer. But this on its own is not good enough. We need to do x equals x plus this. So this is now a residual connection. We're going to take our data and we're going to pass it through all this stuff, add it to itself, and that'll be my new x. So that's my residual connection right there. We can take all of this and do x is self.layer norm x. Very simple. And then we're just going to repeat this again. X is self.feed forward x, but it's add and norm. So we first have to do a residual connection, just like that. And then x is self.final layer norm x, return x, right? So what have we done? Again, as a recap, we did our attention, add and norm, and then our feed forward, add and norm. So we have our residual connections, we have our normalizations, and we are good to go. This is now our RoBERTa encoder layer. And so finally, all we need is the RoBERTa encoder, right? So we can do class RoBERTa encoder, right? The encoder is very simply just a stack of these encoders on top of each other. So again, def init self config. And this config, again, super RoBERTa encoder self dot init. There we go. Self dot config is config. Store that there. And what we need to do is a little bit of effort. So first of all, we're going to do self dot layers is going to be nn dot module list, right? And remember, it's just going to be a list of the RoBERTa encoder layer config. Oh, encoder layer, right? It's just going to be this layer repeated however many times we set the depth. So for blank in range config dot num transformer blocks, right? So however many times we indicated that we wanted these transformer blocks. So there you go. We have our transformer blocks. Now we have to go ahead and write the forward function, right? So again, def forward self x attention mask, by default again will be none. And we have to do a little bit of effort here. So first, let's write batch size by sequence len by embedded is x dot shape. Right, so there we go. What we need to do is if attention mask is not none, right? So this is basically what we had done over at this step. We did these extra unsqueezes and stuff like that. The thing is that flash attention expects the attention in a specific way. So let me pull that up. Scale dot product attention. Here we go. So there's a expectation in how it wants it. So again, in my attention video, I go into detail about this, but if you have an attention mask, what it expects is it must be broadcastable to the shape of attention, which is n by dot dot dot. This dot 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 in our case is head. So this is number of samples by number of heads by the sequence length by the embedding dim, right? So this is kind of its expectation, whatever it may be. So we just need to make sure we actually update our stuff to look like this. So yeah, for example, they have heads by length by E, S by E. Actually, sorry, this should be sequence length by sequence length, right? It's an attention mask. My bad. This should be C. So in this case, they're kind of doing the generic case for cross attention, where your length of your queries and the length of your keys and values are different from each other because you're attending between two different sequences. But in our case, L and S are all the same, right? Everything is the same. So we just need to make sure we update the shape of stuff to be S by S, right? Sequence by sequence, or L by L, however you want to call it. So our data, or our attention mask, let's kind of recap. Our attention mask, if we go to utils, let's print samples and break here. We'll just do it here, so because we actually have data, utils.py. If you remember, this is what our data looks like. Now, I know our attention mask is all one, so we don't really care, but let's just take a look at our attention mask real quick. We're going to have attention mask, and really we care about the shape of it, right? Dot shape. So this should be a 4 by 512, right? Because we have 4 samples and each sample is of length 512. So that makes sense. Now, when we do attention, right, it's going to be in the shape of batch, which is 4 in our case, by heads, by sequence length, by sequence length. Or in our case, it's going to be 512 by 512 because that's the sequence length here. So that's what we have. Batch by head by sequence length by sequence length. Our attention mask is currently just batch by 512. So what we need to do is add some extra dimensions here. So first, we need to add some extra ones. So we need to add a 1 by 1. So it's just the same number of dimensions. We have batch by heads by 512 by 512, and then batch by 1 by 1 by 512. Okay, no big deal. We can do that. We can do dot unsqueeze 0, or actually unsqueeze 1. We want to add it in this dimension. And then we'll do it twice. Dot unsqueeze 1. Right, we'll do this twice. So let's look at the shape. Oh, I should actually look at the shape. Not helpful otherwise. So we have a unsqueeze 1, unsqueeze 1. So there we go. That's our 4 by 1 by 1 by 512. And technically, if we were writing our own attention mechanism, then this would have been fine. This would have been enough information for us to do it. But in the way that Flash attention expects it, it wants it as sequence length by sequence length. So if you remember, let's go back here, right here. If you remember, we kind of explored a little bit of this previously. What we have, let's say this is one sample, right? One sample. So we have token, 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 pad, token, 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 pad, right? So we're doing self-attention. So it wants an attention mask in the shape of 4 by 4 in this case. What we have is just a single vector of 1, 1, 1, and 0, because we want to attend to these three things here, and we don't want to attend to this last token here. So all we need to do is we have a batch. Ignore the batch. This is for one sample. We just have a sequence on the 4 where we want to compute attention on the first three things, and we don't want to compute attention on the last thing. We just need to repeat this 4 times, right? So repeat it 4 times, just to produce our attention mask in the 2D shape. So we can do here dot repeat, and in this case, it's going to be repeat 1 by 1 by sequence len by 1, right? We want to, and we know the sequence len is 512 because we just want to repeat this dimension here by 512. Because again, remember, our attention is a 512 by 512 matrix. It's self-attention, so it's how is every token in my sequence length of 512 related to, you know, all the tokens in its sequence of 512. So we end up with a 512 by 512 matrix of how every token is related to each other. We also repeat this for the number of heads time, but in the Flash attention implementation, it will broadcast the head dimension for us. So we don't care about this so much, but we just need it to be 512 by 512 rather than 1 by 512. Again, this is just how it expects it. There's no rhyme or reason to this. If, again, you have some confusion, I go into tons of detail about attention masks in my attention video. So please just take a look there if there's any confusion. I just don't want to rehash the same thing too many times. But this should be very familiar to here, right? That's basically what we did here. We did 2 unsqueezes, but in my implementation, I left it as batched by 1 by 1 by 512 because I'm writing the attention myself, right? So it's okay. I can do this myself. PyTorch will automatically broadcast this one dimension over the sequence length on its own. Flash attention will not broadcast it for you, so we have to explicitly make this S by S or 512 by 512, right? So just slight differences, but just to give you an idea of how different implementations are slightly different. So we just need to repeat this, right? Let's just repeat exactly this code in our model. So if attention mask is not none, remember the attention mask is coming in as batch by sequence. So batch by sequence length. We need to add those 2 extra dimensions and then repeat that 1 dimension sequence length number of times just so Flash attention is happy. So attention mask is going to be attention mask dot unsqueeze 1 dot unsqueeze 1. We repeat that twice, and then dot repeat 1 by 1 by sequence len by 1. Right? So that'll repeat my batch by 1 by 1 by 512 to a batch by 1 by 512 by 512, right? So there we go. That's just the one quick thing that we need to do. And lastly, we can do for layer in self.layers. We're going to loop through all of our transformer blocks, and we're going to do x is equal to our layer x attention mask equals attention mask. And there we go. And that's basically it, right? Nothing crazy. We have effectively just taken our data. We've expanded our attention mask out just so Flash attention, right? This is a Flash attention specific thing, just so this is happy with the shape of my attention mask. And then all I did is take my data in the attention mask and just pass it through all the different layers of the transformer, and that's it, right? That's basically all we need to do. And we can return X. And this is effectively our RoBERTa encoder, right? The thing that will process everything that we need to do. Now that we have our encoder done, it is time to write kind of basically some helper models, right? We just need to kind of stitch together all the things that we need. So let's first start with our RoBERTa MLM head, right? So what is this? So this is the encoder that will process the text, but we also need the part of the model that will actually predict what is the next token, right? So the actual prediction part of the model. So we're going to call this the class RoBERTa MLM head, right? The masked language modeling head that will predict what is, what is this token supposed to be? What's the correct answer? Def init self config super RoBERTa MLM head self.init. Again, self.config is config. We'll store it here so we can access it if we ever need to. And we can go ahead and write the couple things that we have in our head. So first, self.dense is going, and this will be the prediction head, right? It's going to be a nn.linear. And yeah, so in the implementation, so technically we could just have one linear layer here. In the way that Huggingface did it, I guess they had two different linear layers, so we're just going to follow their strategy, right? So config.embedding dimension to config.embedding dimension. And then we'll have a self.decoder, is what they call it, or we could call it head, it doesn't matter. Decoder is nn.linear config. It'll actually be the same thing. So basically we have two linear layers stacked on top of each other to do our prediction task, right? The masked language modeling task. So there we go. We do add a layer normalization here. So layer norm is nn.layer norm, just like before, config.embedding dimension, and then EPS is config.layer norm EPS. And then we have self.activation is nn.glu, just like that. So we basically have two linear layers with an activation function and a normalization in between them to do our final prediction of what is the thing. And actually this one should be vocab size, right? Because we need to predict which one of the 50,000 whatever possible words is it, right? So there we go. That's our prediction head. And we can just simply pass our data through that. So def forward self inputs, and we're just going to do x is self.dense inputs, x is self.activation, x is self.layer norm, x, and then x is self.decoder x, and we return x, and we are done. So this is going to take the output of the transformer, and it's going to pass it through a linear layer, an activation function, and then our final linear layer will predict what is the missing word, right? So which one of these words is the missing word, and we're done there. So let's go ahead and write our RoBERTa model. So we can do class RoBERTa model, and then .module, def init self config super RoBERTa model self.init. There we go. And again, self.config equals config. And what do we have in a RoBERTa model? Well, we just have two things, right? We have our embeddings, which will convert tokens to embeddings and add the positional information to it. And then we have the encoder, right? The thing that will actually process all the tokens and, basically all of our transformer blocks. So let's go ahead and do that. Self.embeddings is equal to RoBERTa embeddings config. And then self.encoder is going to be RoBERTa encoder config. And all we need to do in our forward function is self input IDs, right? So this will be taking in the tokens, so straight tokens, so input IDs, and our corresponding attention mask, right? And all we'll do is embed our tokens. So embeddings is going to be self.embeddings input IDs. And then our output of all of our transformer blocks is going to be self.encoder embeddings attention mask, just like that. And we can return our output. So simple as that, right? So all I've done is just take all the stuff that we've already written and just kind of glue them together into one model. So this is the RoBERTa model and will act as the backbone to effectively every single task that we care about. So first of all, notice here, HF RoBERTa model, the Huggingface RoBERTa model looks basically like this. It's embeddings and the encoder, right? So that's we have our own RoBERTa model, but there are downstream tasks that we care about that we want to be able to do. Today, we're just going to write one of them. Next time, we'll be writing the one for question answering, right? So today we'll just be doing one of them. We're doing class RoBERTa for Masked Language Modeling, and then .module. But next time, don't know why that happened. But next time we'll be writing a class RoBERTa for question answering, and then .module. Let's throw a pass in there because we're not going to stop doing that. Throw a pass in there. We're not going to be writing this today, but that's what we'll be writing next time, right? So we're going to leave that there. So how do we write our model here? Well, it's very simple. We already did all the hard work, so let's just go ahead and put it together. All we need to do is put our RoBERTa model, and this output will go to the MLM head, right? The thing that will do the prediction task. So let's go ahead and do that. Self config. Again, we need to first do super. RoBERTa for masked LM self.init. There we go. And so first we have to do is, again, self.config is config. And we're going to do our RoBERTa, right? Our actual model will be the RoBERTa model, right? With our config. And then self.mlm head is going to be RoBERTa MLM head with the config. And all we need to do is pass our data through these layers. So very simply, forward, self, we'll have our input IDs, we'll have our attention mask, which is none by default, and we'll also have labels, which is none by default, right? The thing that we want to compute our loss function on, right? So we have our labels because after we pass it through this, we can compute whether or not, what the correct answers are. Basically, that's the idea. What are the correct answers? What are the missing words effectively? So we need our labels to compute that loss function. So let's do our hidden states is going to be self.RoBERTa, and we're going to pass into our RoBERTa model our input IDs and the attention mask, right? So input IDs and attention mask, right? So there we go. This will produce our output of the transformer of how the different words are related to each other and all that sort of stuff. Now that we have that, we can do our preds is self.mlm head, which will predict what is the word that's missing here, right? So that'll be hidden states. Hidden states. So these will be my predictions. And what we're going to do is set loss to none by default, right? And we're going to do if labels is not none. So if labels is not none, we can go ahead and compute our loss. Now, one thing to keep in mind, our predictions here is going to be a batch by sequence by n, where n is the number of possible things, right? N is the number of possible tokens that it could be. So batch by sequence by n. This is what our preds look like. Preds. Our labels, right? Labels. It's going to be batch by sequence, right? What are for every sample, right? For every sample in the batch and for every token, what is the correct answer? Now we know there's going to be lots of negative 100s here, but regardless, these are the correct answers. So all we need to do is flatten it. So we need to convert this to batch times sequence by n and batch times sequence. So we have a vector of correct answers and a vector or a matrix of our predictions. Right, so that's all. We just need to do this quick reshape so cross entropy is happy. The only reason we're doing this is because this is the shape that cross entropy expects. So dot flatten ndim equals 1. So what we have here is 2 dimensions, right? 0, 1, 2. And we just want to flatten everything up to the first dimension. So ndim is 1. So this will produce a batch time sequence by n. So for every sample and for every token in the sample, we have predicted this probability vector, or this, these logits of what is the likelihood of all of the possible tokens in my thing. And then these are my correct answers for this token. So our labels, we can simply do labels.flatten, right? We just go ahead and flatten them because this is batch time sequence or batch by sequence. So we're making a batch time sequence vector. And now that we have that, we can do loss is going to be equal to f dot cross entropy between our preds and labels. And again, ignore index here is by default -100, which is what we set it to, so we don't have to do anything here. But if you, for some reason, picked a different number, this is where you would change it. So this will compute our loss, and we can go ahead and return our hidden states, our preds, and our loss. If we didn't pass in labels, which is fine, right, then we would just return our hidden states and our preds because we have no loss, right? So it doesn't really matter. So there we go. This effectively wraps up our RoBERTa for masked language modeling. So let's see if this works. So let's make this rand int again. A min of 0, a max of, let's say, 1,000. And we need to do a, let's see, size. Let's do a batch size of 4, and each sample of length 512, just like what our data will look like. Let's say our model is going to be this RoBERTa for masked language modeling. And just to make it, it should be fine actually. Let's see if it works. We can do model print model rand. Okay, let's see if this works. Oh, not utils. Python model.py. All right, time to find the bugs. Oh, no, looks like it worked. Okay, so we have our hidden states, right? So we have our hidden states. So this is basically the output of the neural network after the transformer stuff. And then we have our predictions, right? So because we didn't pass any labels in here, right? So we'll test that later when we actually get it. So we can do hidden states, hidden and out preds is this. We can print out the preds.shape just so we can see what it looks like. And it should look exactly how we expect it. It should be 4 by 512. So we have four sentences, or 4 sequences. Each sequence is of length 512. And for each token in the sequence, we predicted the probability vector or raw logit vector of all the possible words it could be, because there's 50,265 possible things this word could be. And hopefully the model will predict the correct word in the correct places. And that's basically it. So that goes ahead. That basically wraps up our RoBERTa, the model implementation. All we have left now is to write our training script. In the next video, we'll come back and actually fill this in, right? So we haven't done that yet. We also haven't done any of this stuff yet to actually leverage like a pre-trained model from Huggingface instead of using our own. So you can kind of follow along in the next video. But for now, this should be totally sufficient. So I am happy with this. Let's go ahead and pull up the last part. We need to write a pre-training script. So let's do that. We're going to write here let's call this pretrain RoBERTa.py. Again, we'll be using Huggingface Accelerate for distributed training because I like using Accelerate. If you want to use something else, then you can kind of adapt this code pretty easily to anything you want. If you're unfamiliar with Accelerate, go take a look at my Accelerate video. And I go into quite a bit of depth there in how to do that stuff. So for this first part, I'm going to go ahead and copy. Let's see. I feel like it would be in our best interest just to copy this. I don't want to waste time. So I'm going to copy this. This is just a bunch of arg parsing. But what do we have here? We have our OS, SHUtil. We'll see why we have these things later. We have NumPy, TQDM, Torch. We have our data loader. We have the accuracy metric from Torch metrics. We have our load from disk to get our data. We have our scheduler, seeds. We have our accelerator here for the distributed training part. And then we have our, what do you call it? we have our utils. We created a RoBERTa config, right? And we also wrote our Collate function, so we're going to need those things. And we also have here our model and our RoBERTa for masked language modeling, right? So basically everything we've done. I'll quickly go through all these. So this is my typical setup. What is the name of the experiment that we're running? What is the working directory where we want to save things like checkpoints and stuff like that? So these are my argparse, basically. What is the name of the model we're using? If we are leveraging, in this case, we're going to be using it for the tokenizer, but what is the model we're using from Huggingface? We have our dataset stuff, right? So context length, masking probability, number of workers, path to prep data, right? Where we saved the data earlier. We then have all of our model arguments, right? So again, all of this stuff was in the config, but it's here. In case you wanted to change it through the command line, which is typically preferable. So there we go. Hidden, dropout, we have our attention, number of transformer blocks, number of attention heads, the embedding dimension, the multi-layer perceptron ratio, layer norm, and the initializer range, which actually reminds me, we never did that. So let's go back real quick and do that part. We need to write a different weight initialization strategy that is very simple. It's just I don't know how much it matters, but I'm just trying to follow typical how it's done. Module. Weights are typically initialized for transformers with a standard normal distribution. So we're going to be doing that. So let's go ahead and do if is instance module and then dot linear. So we're going to apply this function here to our model, right? To our RoBERTa for masked language modeling. And the thing is that when we apply this, what we want to do is if you're a linear layer, right? So if this module is a linear layer, it'll apply it recursively all by itself. But if it's a linear layer, then what we want to do is module.weight.data. We want to initialize it with a normal distribution with a mean of 0 and a standard deviation of 0.02. And that's the typical kind of setup for most of these transformer initializations. Sometimes they'll use truncated normal instead of regular normal, but I don't know if there's a huge difference. Either way, this is mostly just taken from the Huggingface implementation, so there you go. And we're going to do if module.bias is not none, right? So if there is a bias, which there is for all the layers we did, we're going to initialize all the biases as 0. So module.bias.data.0. Right, so there we go. If elif is instance module, and if this is a nn.embedding layer, which it could be, we're again going to do module.weight.data.normal. Again, mean will be 0, STD or standard deviation will be 0.02, and we will do a if module.padding index is not none, right? So if we have which we did, right? We have our padding index, which of these tokens is padding. We're going to go ahead and just set the padding thing to 0. Because we set the padding index as something in the embedding matrix, this thing will never get gradients. We don't really care about it. It doesn't mean anything. It doesn't do anything. So we're just going to set it to 0 because it doesn't really matter. So module.weight.data module.padding index, so wherever that is, we're going to set it to 0, so .0. There we go. And then lastly, elif is instance module nn.layer normalization, so layer norm. Again, very similarly, we're going to do module.bias.data.0. So we're going to go ahead and set all of the means, which is the bias, to 0, and we're going to set all the standard deviations to 1. So module.weight.data.fill with 1.0, right? So there we go. We just set the means and standard deviations to 0s and 1s, and that will be our weight initialization. And so we can simply apply that right here. We can do self.apply init weights. So there we go. We have our weight initialization. Set another underscore right here. There we go. So this will reinitialize the model weights for the RoBERTa model and the MLM head with this initialization strategy. How much it matters, I don't know, but I'm sure there's a reason for it, so we're going to leave it like that. Good. Okay, so now going back to our thing, we have initialization. We actually never passed this in because I hard-coded it here, but it's fine. Don't worry about it. We then have, standard training configuration. What is our batch size? How many grain accumulation steps do we want to do? How many training steps do we want to do? I set it to 250,000. I think that's the default, what they use, but I was only personally able to train it for 75,000 steps, which is probably fine. This is just a proof of concept anyway. You need way more resources to train it for 250,000 steps, but that's fine. We have our max grad norm, so gradient, we'll do gradient clipping, how many warm-up steps, the learning rate scheduler, logging steps, how often do we want to print to console, and also store in weights and biases so we can see how training's going. We have our evaluation interval, how often do we want to evaluate on the testing data, checkpointing, learning rate, all this extra stuff. I'm going to ignore this today just to make this a little bit simpler, so don't worry about that. We have our weight decay, right? So on the Atom W optimizer, or our weight penalty effectively. We have our Atom beta 1 and beta 2. These are the beta 1s and beta 2 that they use, so that's why I'm going with these numbers here. We have our epsilon, that's fine. How many checkpoints do we want to keep? If you're training for like 200,000 steps, each checkpoint will take up quite a bit of disk space because this model is relatively large, so you don't want to end up with like 100 or 200 checkpoints, so we can just kind of delete older checkpoints as we're going. And then we have our seed, and then resuming from checkpoint, and whether or not you want to log to weights and biases. So again, this is just me copy pasting in just kind of housekeeping stuff that isn't really of interest, but it's there because we're gonna need it. And then similarly, I'm going to go ahead and copy paste this script into here. So we're going to create a pretrain.sh, and here we go. We have all of the, basically everything in that arg parse is set right here, right? All the parameters that we want to use for everything that we want to do. I'm going to set this to RoBERTa. Actually, this is probably fine. I'm going to get rid of the weights and biases because I have no need. I've already trained this, so I don't need to log it again. We have our seed is fine. And we just need to go ahead and create a new folder in here called workdir. So that's my working directory, right? Where I want to save my checkpoints as I'm going. Okay, good. So I think that should be sufficient for now, just to make it a little bit simpler. We'll see whether or not there's any errors because I deleted some stuff from the arg parse, but we'll get there later, so that's fine. All right, so let us now go ahead and write the pre-training script. So it should be relatively simple, nothing too crazy. We're going to do args is going to be parse args, and for now, actually, instead of doing accelerate launch, instead of running in multiple GPs, we're just going to do Python to keep it simple, right? So we're going to do that so everything's running once. Okay, let's print out the args, make sure this works real quick. Python actually we need to do bash pretrain.sh, right? So let's see if this works. Nope. So there we go. There is all of my argument parsing. I just turned weights and biases off because we're not going to need it today because I'm not going to be actually fully training this model. This is just a demo. Okay, so we're going to do if args.seed is not none, right? If we don't have a seed, we can use the set seed function that we imported from accelerate, right? We can set the seed right here, or from transformers, right? This will set our CUDA seed, NumPy seed, basically all the different seeds that we care about. So if we pass in a seed for reproducible training, there you go. And we're going to give it args.seed. Right? Oh, sorry about that. Now that we have this, we can go ahead and do the rest of the stuff. And a lot of this should feel very familiar because we've done this 1,000 times. Path to experiment is going to be os.path.join. Right, we're going to store our path to experiment will be args.the working directory that we set to the args.experiment name, right? And our accelerator is equal to the accelerator. And it's going to have our project directory is path to experiment, and log width is going to be weights and biases if args.log weights and biases, else none. Right? Otherwise, we won't be using anything logging. Also, notice here that I included gradient accumulation somewhere here. I can't remember, but we have gradient accumulation happening, but I didn't put it in here. So in one of my previous videos, when we talked about accelerate, let me pull that example up really quickly. So this is an example of using accelerate to train the ResNet model. When we defined the accelerator, which we did right here, we included a gradient accumulation steps because we were using the accelerator.accumulate context manager to do our gradient accumulation. You can do it this way. You can also not do it this way. So today we're going to not use it just so you can kind of see different ways of doing exactly the same thing. But when we don't use this accelerator.accumulate, we need to manage the gradient accumulation ourselves. So again, this is just to show you some different ways of doing exactly the same thing, so you're not really dependent on doing something in a very specific way. So there we go. And we're going to do if args.log weights and biases, then we can do accelerator.init trackers, args.experiment name. So if we're using weights and biases, right, we're logging, and then we can initialize it here. There we go. Similarly, our tokenizer is going to be the RoBERTa tokenizer fast dot from pretrained, and it'll be args.hf model name, right? So that's my tokenizer. Good. I'm going to copy this part in because I don't want to type it, but this is basically my config. So this is the same config that we wrote right here, but instead of just directly using the defaults, I'm passing in all the stuff I need from my tokenizer and basically all of my arguments and stuff like that. So this is just my config. That's it. So we can take a look. Print config, make sure this works. This should work just fine. This should print out. There we go. So that's my RoBERTa config, as you can see, with all the stuff that we have. Oh, it looks like the pad token is 1 and the end token is 2. So I guess I got that wrong. So it's a good thing that we're doing this. Sometimes they'll be the same, but sometimes they're different. There we go. Let me just fix that. Okay. Okay, good. So that's our config, right? Nothing crazy. And now we can go here and load our data the way that we had done it before. So here we were testing our stuff. So we can go ahead and load our data in this way and then do all of this stuff exactly the same way, right? So loading our data, creating our data loaders. So first of all, our data, or let's call this, keep it the same, tokenized data, is going to be stored in args.path to prep data, right? That's my data set, right? And we don't need you anymore. We already are passing in our config right here with our masked language model, our collate function, right, that we wrote. And then we will have both a train loader and a test loader, right? So let's go ahead and do that. Our train data loader is just going to be our data loader on our training split of the tokenized data. But we have a couple extra little things to do. First of all, the batch size is not going to be whatever the batch size it's set. It's going to be our, let's create it, mini batch size. It's going to be args.per GPU batch size. So how many samples do we have per GPU? Split up by the gradient accumulation steps, right? Gradient accumulation steps. And why are we doing that? It's because if I can't fit a batch size of 64 on my GPU, I might be able to split it up into maybe 4 different steps and fit batches of 16 on the GPU every single time. So I'm just doing mini batch sizes of whatever that is. So there we go. Our collate function is a collate function, and the num workers is going to be args dot, what did I call it? Let's see here. Num workers, let's see. Here we go. args.numWorkers is what I called it. So there we go. args.numWorkers, and that will go ahead and be our train data loader. The test data loader will be identical. I think I called it test, or I called it eval. Okay, eval data loader will be identical, except this will be on the testing split. And there we go. And we also want to make sure we do shuffle equals true here, right? We want to shuffle our training data, but we can turn shuffle to false here because we don't really need to do that on this one. Good. So we now have all of our data ready to go. Another thing that could be of interest is, or actually not of interest, we need to first load our model here as well. So let's go and do that. Our model is the RoBERTa for Masked LM config, right? There we go. That's our model. We can print out our model real quick. Let's make sure we can actually take a look and see what our model looks like. So there's our model, right? So we have our embeddings, we have our encoder, which is a bunch of layers of attention, feed forwards, yada, 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 right? So that's our model. One thing that's typically of interest is how many parameters am I training? So I'm just going to paste this in. This is going to filter out all of the parameters in our model that require grad, which should be all of them. Everything's trainable here. And then we're just going to add up the number of parameters and just print out how many parameters are we working with here. And this should print out some, I don't know. Looks like we're training a 1, 2, 3, 1, 2, 3. So 163 million parameters. Okay, not a unreasonably large model. It's fine. Okay, so we now have our model. We have our collate function. We have our mini batch size. We have our train loader, data loader. What else do we need? Right, we need our optimizer. So we can do our optimizer. It's just going to be our torch.optim.atom.w. We're going to do model.parameters. Our learning rate is going to be args.the learning rate that we set. It doesn't matter. We're going to have a scheduler in just a bit, but it's fine. And then our betas is going to be args.atom beta1, args.atom beta2, right? So there we go. Those will be the beta1, beta2 parameters of our thing. And then EPS is going to be args.atom epsilon. And I got my numbers basically from the RoBERTa paper, so that's the only reason I made these decisions for these numbers, right? So there we go. Now that we have all of this ready to go, we can go ahead and do scheduler is going to be a get scheduler. So get scheduler is a nifty little helper from Transformers that will just let me grab a scheduler based on the name. In my case, I will be using a linear scheduler. So that's what we're doing. So we're going to do a name is going to be args.lr scheduler type, right? Which is what we called it right here. Let's just look it up, scheduler type. So we're doing linear. We could have also done one of the other ones, but I think I just found they use linear in the paper. I can't remember off the top of my head, but that's what we're going with. So we have our scheduler. We have to tell it the optimizer is going to be our optimizer. How many warm-up steps do we have? Num warm-up steps is going to be args.num warm-up steps, and then training steps is going to be args.num training steps. And there we go. Right, so that's our scheduler. Everything's ready to go. And so all we need to do now is our model, optimizer, train data loader, eval data loader is going to be accelerator.prepare model, optimizer, train data loader, eval data loader, right? So again, just like everything in when using accelerate, we need to actually convert everything from regular models, optimizers, and stuff to a DDP version of it. And that's what the accelerate will do for you. So now that we have all that, and we also want to make sure if you're, we need to resume from checkpoint because you're training your model, your Slurm script ends, something goes wrong, the power goes out. You want to be able to pick up from where you left off, which means we want to make sure we're also we're checkpointing our scheduler. So we're going to do accelerator.register for checkpointing scheduler. Right? We're going to make sure that's also saved as we're checkpointing our model so we can pick up exactly from where we left off. Lastly, we need to be able to compute the accuracy. Accuracy doesn't matter as much when it comes to these types of models because when you're filling in the blank, technically there could be multiple words. That's like a valid fill in the blank for your masked language modeling task, but accuracy kind of gives you a general idea of if the model's improving or not, so I'm just going to include it. Although it's definitely not a good metric, it's just kind of just lets you know that things are working. So task is multi-class. Num classes is going to be tokenizer.vocab size. And then ignore index will be -100, right? We don't need to compute any accuracy on things that were not masked, right? So there we go. And this just needs to be sitting on the little code for this needs to just be sitting on the same device as the rest of this stuff. So we're going to make sure it's sitting on the device for this specific GPU when we're training on multiple GPUs. So accelerator.device. Good. Now we need to write the quick little helper function for resuming from checkpoint, if that's what we need to do. So we're going to do if args.resume from checkpoint is not none. So you actually pass something in for it. Our path to checkpoint will be os.path.join. It's going to be stored in our path to experiment, and then the name of the checkpoint, resume from checkpoint. So I've talked about this before, but typically what I like to do is checkpoint stored like checkpoint 10,000 and then checkpoint like 20,000 or whatever, like in whatever interval it's happening. So I like storing my checkpoints like this. And so inside my folder, path to experiment, I will have a checkpoint folder, right, for this checkpoint. And inside this checkpoint folder, I'll have the model saved and the optimizer and everything else. Everything will be saved inside that checkpoint folder. Now that I have that, what we need to do is just load that checkpoint, right? So all we need to do is with accelerator.main process first, which is just a recommendation from Huggingface that whenever you're loading a checkpoint, you should do it on the main process first. We can do accelerator.load state path to checkpoint, just like that. And finally, let's say you're training for 200,000 steps. And what you're doing is, let's say you train for 20,000 steps, then you want to pick up from 20,000, right? Just like before. So what we're going to do is completed steps is just going to be args.resume from checkpoint, which is just this, right? Args.resume, this thing here, args.resume from checkpoint, will just be this string, checkpoint 10,000. So all we need to do is grab this number here, 10,000. So we can do .split underscore and grab -1, right? That will give me the 10,000, and we can just convert this to an integer. And this will effectively just let me figure out how many steps have I already completed. Simple as that. And so then we can do a quick accelerator.print resuming from checkpoint, and we can do completed steps, which will let me know in the console that we're actually indeed resuming from the checkpoint. If we're not resuming from a checkpoint, so else, we just do completed steps is 0, right? Because we're starting right from the beginning. And so now, just like always, we're going to set train to true, right? So we're going to set a flag here for training. And we're going to do a progress bar. Progress bar is just going to be TQDM range from completed steps to args.numTraining steps, right? So by default, it'll go from 0, right? If there's no, but if we're starting from 10,000, then it'll start from 10,000 or whatever it may be. And we'll do disable is equal to not accelerator dot is main process, right? So we only want to print out the progress bar once. If we don't have this, then it would print out for every single GPU that we have, and that wouldn't be helpful for us. So this will just print it out once, and we're good to go. And so now let's go ahead and write a very, very simple training script. There's really not much to do here because our loss and everything is kind of being done inside the model, but there is one thing. We need to kind of do the gradient accumulation manually. And it's pretty simple, but just a little bit of effort on our end. So while train is true. What we're going to do is accumulate steps is 0 by default, right? So how many steps of accumulation have we done? Accumulate loss is 0, right? We're going to be kind of keeping track of stuff. And then accuracy is 0. This should also be, let's call it accumulate accuracy is 0. Yeah, that should work. Okay, let's go with that. Okay, so this is basically me keeping track of how many accumulation steps have I done, what is my accumulated loss, and what is my accumulated accuracy, right? Simple as that. And what we're gonna do is for batch in train data loader, right? We're on our training loop. Batch is equal to, and this is a quick helper. So remember our batch is a dictionary of this stuff. So if we look at our utils, right, it's a dictionary of input IDs, attention, mask, and labels. All three of these things need to be on the GPU, right, for us to be able to train our model. So if we want them to all be on the GPU, we can just use dictionary comprehension and just put everything on the GPU. So we can do here kv for kv in batch.items, right? So this is just me looping through every key and value. So keys and the actual tensors in my dictionary. But for the v's, I'm going to put them on the .to accelerator.device. Right, so there we go. I just want to make sure that my input IDs, my attention mask, and my labels are all sitting on the correct GPU, just like that. And so very simply, we're going to have logits, preds, and loss is model, and we're just going to pass in our batch, right, to our model. And we know it's going to return all three of these things because in our model, we specified if the labels is not none, which is not because we're passing it in, then there you go. We have all three of our things right there. And now that we have all of that, we can go ahead and we have our logits, preds, and loss. We can now go ahead and do the things we need to do for the fact that we're accumulating. So what we're going to do is loss is equal to loss divided by args.gradient accumulation steps. Because what we're going to, and actually it'll make more sense, we can do accumulated loss plus equals loss. So what we have done here is we are effectively just keeping track of the average loss, right? We just want to average up our loss across all these accumulation steps, right? So to do that, we just need to do this, right? Just averaging up, dividing by that. We now need to compute our gradient. So accelerator.backward loss, right? Go ahead and compute our gradients. Similarly, we need to compute our accuracy. So we can do our labels is equal to batch labels, right? I'm just indexing out, the labels from here, and we're just going to flatten it real quick, right? So we basically have a vector of all the possible labels, including the negative 100s, but we don't really, like we mentioned before, we will be ignoring negative 100, right? So we won't be computing accuracy on things that are negative 100. So our accuracy func, right? Our accuracy is going to be the accuracy function that we have earlier from torch metrics. We're going to give it our predictions and our labels, right? And that's enough for us to calculate the accuracy. And again, we got preds from here, right? The direct predictions from our model. It's already been flattened and ready to go, so there's really nothing left for us to do here. So that's enough for us to calculate the accuracy. Now that we have that, we can then do our accumulated accuracy plus equals accuracy divided by args dot gradient accumulation steps, right? Just average up the accuracy for our full accumulation. And once we have done all of this stuff, right, we have effectively completed a single accumulation step. So we can do accumulate steps plus equals 1. We have completed one accumulation step. Notice that we haven't done any optimizer.step and that's it. We haven't updated the model. We've simply computed gradients and that's it. Now that we have done all of this stuff, accumulated gradients, that sort of stuff, we now need to actually update the model. So we're going to do if accumulate steps, or accumulate steps percent args dot gradient accumulation steps. So what this is doing is, let's say we're doing a accumulation of 4. So we're doing 4 accumulation steps. We're basically going to repeat this code 4 times, and accumulate steps will go from 0 to 1, 1 to 2, 2 to 3, 3 to 4. And then once it's 4, right? Once we've completed 4 accumulation steps, equals 0, we can now update the model. Like we have completed however many accumulation steps we needed. So now we can go and update the model. We can do first accelerator.clip grad norm model.parameters and args.max grad norm. So again, this is always a good thing to include just in case there's some kind of an exploding gradient or something like that. Go ahead and just clip your gradients to whatever the max grad norm is. Now that we've done that, we can do optimizer.step and optimizer.0 grad, right? And we can do a better version, set to none equals true. So this has gone ahead and finally updated the model with all these accumulated gradients that we just made. Once we have done that, we now need to also update our scheduler, our learning rate scheduler, right? So in this case, we have our learning rate scheduler. We just need to update it. We need to step it, so we can do scheduler.step. And also remember, we didn't scale our scheduler by the number of gradient accumulation steps or anything like that, like we've done in past implementations. The reason is because I'm doing it manually here. So I only step when the accumulation is done. So I'm effectively doing the correct number of steps, whatever it may be. So there we go. We have updated our model, step through our scheduler, and now it's time for us to log results if we want to. So we can do if completed steps percent args dot logging steps is 0, right? So if we want to log, now we can do our accumulate loss is accumulate. Is that what I called it? Yeah, accumulate loss dot detach, right? Take it off the, we don't need it to have any gradients or anything attached to it, so we can do that. And we can do accumulate accuracy is going to be, again, accumulate accuracy dot detach. No need to have this connected to anything either. And one thing we need to do is if accelerator dot num processes, right? So if we're training on multiple GPUs, if the number of processes is greater than 1, then we need to grab the accumulated loss and the accumulated accuracy from all the GPUs, gather them, and average them. So we get an overall across all the GPUs, what is our accumulated loss, what's our accumulated accuracy, that sort of stuff. So this only applies if you're training on multiple GPUs, but that's what we're doing here. So we're going to do accumulate loss is equal to torch.mean, right? We're going to average up accelerator.gather for metrics accumulate loss. So this will effectively grab this variable accumulate loss from all the GPUs. So if you're training on 16 GPUs, it'll grab all 16 losses from all 16 GPUs and just return a tensor with 16 numbers in it for all those 16 values. And then for those 16 things, all I want to do is just average it all together so I get the overall across all the GPUs, what is my aggregate loss. And we're going to do exactly the same thing for our accumulate accuracy, right? So we're going to take our accuracy, we're going to gather them across all the GPUs, and then average up what's my overall accuracy for all this stuff. So there we go. And so finally, our log is going to be train loss, accumulate loss. We'll have our train accumulate accuracy, and then our learning rate. And we can do scheduler.get last LR 0. So this will just tell me what the last learning rate was on that scheduler and just print it out. And so finally, I'm going to just copy this. So I have to type it all out, but this is just a simple logging string, right, that I want to print to console. Where are things at, that sort of stuff. And this should be accumulate accuracy. There we go. So it's going to print out how many steps are completed, how many are left, and then my training loss and my training accuracy to console, just so I can see it happening. And we can do if accelerator dot is main process. We can do progress bar dot write logging string, right? So we're going to use the progress bar, write it there so it doesn't mess with the progress bar. And then we're going to do if args.log weights and biases, right? If we want to log the weights and biases, we can do accelerator.log log step equals completed step. So this is me just storing these values in weights and biases so I can visualize it through their nice little graphs and stuff that we'll take a look at a little bit later. So this is effectively it, right? This is all we need for training. Now we just need a couple extra things. We want to, run an evaluation loop and that sort of stuff. So let's go ahead and write that. So this is if accelerator logging steps. After we do a logging, we can now check for another thing. We can do if, let's see, completed steps percentage args.evaluation interval is 0, right? So if we're in evaluation mode now, we can now do if accelerator dot is main process. We can do progress bar dot print, and we can write evaluating model, right? So now we're doing a evaluation of our model. If we're evaluating our model, that means we're throwing the model into evaluation mode. Once we're done, we're going to throw it back into training mode, right? So we're going to have that just so we don't forget. And so very simply, log is going to be val loss. It's going to be 0. And then we'll have val ac. Again, it's going to be 0. And we're just going to add to these. So we're going to do num losses is 0. And honestly, I can just copy this because this code is not that interesting. It's exactly what we've done so far. Right, so we're going to loop through our evaluation data, grab our batches. We're going to accumulate together all of our stuff if we have it, add it to our thing, and then at the very end, we want to make sure we take the average over the entire evaluation set. So there you go. We're going to divide by the number of losses, and that's basically it, right? Nothing crazy. Oh, and we should actually have another one of these right here. If we're greater than 1, then we also want to make sure we gather our accuracy, just like that. I should fix that in my main code. I'll fix that later. So this is, again, nothing has changed. We're just inferencing our model because it's in evaluation mode, looping through, counting up how many batches we just passed through, average it all together, and then just iterate the number of losses so we can then just scale our final results at the end. And then again, I can just print out this. I can just add this logging string right here. And actually, I'll just paste the rest of this. It doesn't really matter. This is exactly the same code as before. We have a logging string. We're going to write to console, how is the validation loss going? And then we can also store this in weights and biases, exactly how we've done it before. And that's basically it, right? This is our training loop with a evaluation interval and that sort of stuff. Now, the last part is checkpointing, right? We want to make sure as our model's training, we're saving checkpoints, because if the power goes out, it would suck to lose all your work. So we want to make sure we do that. We're going to do completed steps %args.checkpoint interval is 0, right? So every checkpoint interval, we're going to do path to checkpoint is going to be os.path.join. We're storing our checkpoints in the path to experiment, and we're going to call the checkpoint folders, just like I mentioned before. We're going to do checkpoint _ completed steps, right? So that's how I will be indicating this is the folder for this specific checkpoint. You can also have the accelerator auto name the checkpoints, but this way it's just simple. So there you go. We're going to do if accelerator.is main process progress bar dot write saving checkpoint to path to checkpoint, just like that. And so now we can go ahead and do accelerator dot wait for everyone. We want to make sure all the GPUs are caught up at this point, right? They've all made it to this step. And once they have, we can go ahead and save our final checkpoint, right? This current checkpoint. So we can go ahead and do if accelerator.is main process. We actually might not need this, but it's fine. Accelerator dot save state. We only want to save this once, so we're going to do it on the main process. Output dir equals path to checkpoint, just like that. So this will go ahead and save our checkpoint. The next part is a little bit finicky, but it's probably important in case you want to do it. We can do if args.num keep checkpoints is not none, right? So, let's say you are training for 200,000 steps and you're checkpointing every 1,000 steps. That means at the end of training, you should end up with 200 checkpoints, which might be too many. Maybe you only want like the newest 10, right? The last 10 of them. So that's all we need to do. We can just do if accelerator dot is main process, right? So on the main process, we're going to do all checkpoints. It's going to be os.lister path to experiment, right? So this will create a list of all the checkpoints in our thing, but we want to only keep the last however many of them, right? So what we need to do is just delete. We need to first sort them and then do it that way. So we first need to sort them. We can do all checkpoints is equal to sorted all checkpoints. And we want to sort them by key equals lambda x, right? So you can simply do it this way. And what we're going to do is take x dot split on the period. Where does this period actually come from, if I can remember? It's kind of hard to do this without an exact example, but maybe we can fake it. Here, let's just create some. We're gonna create checkpoint 0, and then we're gonna create another one, checkpoint 50, and then new folder, new file. Sorry, new folder. Oh, I nested it. My bad. New folder, checkpoint 50. Oh my god, I have created so many nested folders. 1 second. Let me delete this, delete this. Okay, here we go. Checkpoint 50, and then we'll have another one, new folder, checkpoint 100. There you go. So what we're going to do is if name equals main, print os.lister work dir. And for now, I'm just going to comment everything out here because we don't need any of you to do this. Sorry, this is just me double checking what I've done. So if double underscore, and in this case, we can just run pretrain RoBERTa.py. Here we go. So notice here, it actually doesn't sort by the number, right? We have 0 and then 100 and then 50, and that's not helpful for any of us. So what we're going to do is this would be an example of all checkpoints. And then we can do all checkpoints. Let's print. Actually, we want to do sorted all checkpoints. All checkpoints is that. And even if we sort it, right, all checkpoints, what you'll end up seeing is this, right? It doesn't sort it exactly correctly, right? So we need to sort by this key. And so what we can do is put in a key equals lambda x, and then we can do x dot split on the underscore, right? And then we can grab the last number, right? So grab the numbers and then convert these to integers. And this will correctly sort. So 0, 50, 100, ... So this will correctly sort it. So this is what we want to do. Okay, good. It's always easier to do a little bit more with an example, but there we go. I don't know why there's a period here. I need to check on that later, but for now this should be fine. So we're going to just copy this into here. So there we go. So we've gone ahead and we have sorted our checkpoints correctly. Now that we have all the checkpoints, we can do if len all checkpoints is greater than args.num keep checkpoints, right? So if we've exceeded the number of checkpoints that we want to keep, then we will do checkpoints to delete are going to be all checkpoints, and we want to keep only the last args.num keep checkpoints, right? Those are the ones that we actually want to keep in the end. And then we can do for checkpoint to delete in checkpoints to delete. We're going to loop to all of them. We're going to do path to checkpoint to delete will be os.path.join. We're going to throw a path to experiment checkpoint to delete right here. And then we can do if os.path.isdir is just a sanity check. As long as it's a directory, path to checkpoint to delete, then we can use the shutil.rm tree path to checkpoint to delete, right? So this will go ahead and delete any checkpoint that's not the ones that we want to keep. So if we set this to 10, for example, then we'll only keep the last 10 checkpoints as we're going. And we just want to make sure that all of this is complete before we continue on. So we're going to do accelerator.wait for everyone, right? This will just make sure that we're waiting for everyone as the main GPU is going ahead and deleting any extra checkpoints that we don't want. And that should basically cover it. There's one more thing just to wrap it up. If completed steps greater than or equal to args.num training steps, right? So if we have that, we can do train equals false. If accelerator.is main process, we can do again progress bar dot write completed training, right? So we've completed training. And we've set train to false. So when I throw a break here, it will exit the loop here, and then it'll exit this, and then the while train basically will, train is now false. So the while loop also breaks. And so we are now effectively done, right? We have completed everything and we are good to go. So at the very end, all we need to do, and let me just double check that I have my indentation correct, because that's a common place to mess up when there's so many lines. We have the for loop here. Yeah, okay, we're good. And then also remember, once we've completed a full accumulation step, right? Once all of this is done, that means we have actually completed a global step, right? Like a full step of our training has been completed. So we can do completed steps plus equals 1. Progress bar dot update 1, and we can now set our accumulate loss as 0 and accumulate accuracy as 0. So we're going to reset them. So the idea is that, again, as we're training, we only really complete a full step once we finish the accumulation. So only once we have actually accumulated enough of these steps have we completed everything else, right? So we've completed a full step. We can update the progress bar to update by 1, and we can then go ahead and reset our accumulated loss and accumulated accuracy back to 0, right? So we can start up from where we left off. We could also set this to 0, but this will just keep adding 1 over and over again. So every accumulation steps, it will be divisible, so it's fine. And once all of this is finally done, we can do accelerator dot end training for a clean exit to our DDP. And that is basically it. That covers an entire training script, to at least what I used to train this model. Let's give this a try. Accelerate launch. Actually, let's do Python first, just because there's probably a bug in here and I want to make sure we see it. Actually, bash pretrain .sh. There we go. Okay, so yeah, we're just going to make sure this is working with Python, and then we'll move over to DDP in just a second. So it looks like I'm training for 300,000 steps. Yeah, of course that's going to throw an error because we're not using any kind of mixed precision when just doing regular Python. Let's make the batch size. Where do I set the batch size? Let me check here. I must be, oh, yeah, I'm just being blind. Okay, let's make this 16 for now, right? So just, it doesn't matter. We're just like testing stuff here. So here we go. All right, looks like we have so it should not be progressbar.print, it should be progressbar.write. So it looks like we are already, something happened. So let's take a look in our pre-train. We can do progressbar.print. This should be right. Okay. Let's see now. So this will do a step. It will do an evaluation, and then it will keep going basically. So let's go ahead and now actually leverage a little bit more. Let's see if it works in DDP mode. So we're going to do accelerate launch instead. We have everything else is the same. So let's just go ahead and do this. Let's see if this works. Okay, good. So you can see it's going much faster, about 2 minutes in DDP mode. We can also verify. So let's go ahead and do one more thing. Let's just add a sanity check here. We don't really need to evaluate on the very first step, even though I did it that way. And completed steps does not equal to 0, right? So there's no real reason to evaluate on the first thing, actually. Okay, that's fair. We actually wouldn't even want a checkpoint on the first thing, so let's just add a couple of these checks in. So let's add you. There we go. So no need to do that on the first step, just so we can see it train a little bit without evaluating. Let's check now. Otherwise, I'll just comment that section out if this is still being a little annoying. Good. There we go. So we can see with the batch size that I picked, pretty simple. It's going to take very quick, but obviously we want to use larger batch sizes when we can. So let's make this 512. I don't know if I can do 512 on my current GPUs. Let's just check. So we want to train batches of 512, but with 8 accumulation steps, right? So that gives you an idea. Still out of memory. So let's drop you down to 256. Ideally, you wouldn't drop down the batch size. You'd actually up the accumulation steps, but either way. There we go. So yeah, this model will take roughly, I think it would take 250 hours to train it for the 300,000 steps that I have it set to. That obviously is not feasible for me. I don't have the resources currently to train for that long. So I created a dummy example where we just trained it for about 75,000 iterations, just to get some evidence that it's working. I also can't match the batch sizes and stuff that Facebook can do, obviously, because that would be crazy. That requires, I think they trained on maybe 256 GPUs or something like that for these models, which I don't have access to personally, right? So, but we can see the loss is decreasing, right? We're getting some evidence of learning, 9.7, 9.6, 9.5. If we take a quick look at NB top, right, we can see both GPUs are being hit. They're actually not as hard as that they could be. So I could have probably reduced the accumulation steps and get a little boost in speed, right? So it could be using more of the memory, but the model is indeed training. We can see now it's down to 9.0. So we're getting some evidence of learning here. And what I want to do now is mostly show what some of these final results look like if you were to actually train this model yourself. So let's first find the RoBERTa pre-training. Here we go. RoBERTa pre-training. Okay. So yeah, we can see it's decreasing. So clear evidence. And we can also start to see that the quote unquote accuracy, although again, accuracy is not a good metric for this, is indeed increasing. Like it's getting better and better at being able to identify what the correct word is. This is also a good opportunity where like label smoothing could be a good option, because when you're not 100% sure what the word could be, when there's multiple options for what the word could be, the missing word could be, then label smoothing will help the model avoid overfitting to specific words fitting in specific places. So either way, this, I'm going to stop it for now because this is obviously not interesting to see. What's more interesting is this. So this is kind of what the final results looked like. I had a spike here, as you can see. So this is why it's great to always have some type of what do you call it? The gradient clipping, because this spike here will completely ruin training, right? So you want to make sure that you're handling clipping, because spikes can happen, right? Things can always happen. Okay, so we have kind of the successful training, right? We can kind of see this seems like a reasonable thing to do. If we look at it without clipping, basically I was training, the spike happened, and it effectively destroyed my model, right? So accidents happen, mistakes happen. This is why gradient clipping is just a really good sanity check to always have in your model. Otherwise, you'll end up kind of, losing work and GPU hours that you just put all this time into. So we can see that the model's training, I obviously could not reach 300,000 steps. I didn't have the resources for it. So this is a model that was trained for roughly 75,000 steps. It could be better. There's still opportunity for this model to continue to learn. It's not overfitting, as you can see, the validation loss, or it's not overfitting in any meaningful way. So this model could continue to learn interesting things because we trained on a pretty large data set. Wikipedia plus book corpus is a reasonably large data set. So now that we have all of this kind of ready to go, let's take a look at, the model itself is not that interesting just yet, because the model we just trained is effectively just a fill in the gap model like we've seen before. So I can just kind of show this. I don't even need to run it. So we can kind of look here. Actually not here. I wrote a inference MLM. So just like before, right? I wanted to see whether or not the model could actually, predict something reasonable. And so I just loaded the model, right? The path to the weights, gave it the config. I loaded my model here, model.static. I like saving, actually the accelerate, when you do save state, it'll always save the model as safe tensors. Safe tensors are really convenient ways to do it, and we can load them using this here, safetensors.torch, import load file. So I can load this here. So I loaded the path to my weights. I loaded those weights to my model, stored the set the model to evaluation mode, and then I just gave it a let's play a mask of chess, right? And this should look very similar to the inference script we wrote earlier for the Harry Potter stuff that we did, but it got let's play a game of chess, which is a very reasonable guess for what this should be, right? So either way, I hope this gave you a good idea of how we can potentially reproduce RoBERTa, or in general reproduce masked language modeling. Masked language modeling is pretty generic, and it's used in all sorts of stuff. Later on, I want you to keep this in mind, because when we start doing vision transformer, the vision transformer itself actually isn't all that interesting. You probably understand 90% of what you need for it. There's basically just like 5 lines of code that make the vision transformer, but everything else in the model will be very close to the same. So you shouldn't be too concerned about that. The more interesting strategy actually is the masked autoencoder, which does the masked language modeling just in a different way. And we'll be exploring that hopefully in the coming weeks. Either way, this effectively, again, you can take a look if you want to do this yourself. You can run my prepare script, you can run my model, you can basically do all that stuff, right? You can this part we have not done yet, right? Fine tuning for question answering. Just to show some evidence of learning, right? So when we actually do question answering, a typical benchmark is called the squad benchmark. And so we see that, and we'll see specifically how we build this next time, but we see that my model, we get a loss of about 0.81 with the Facebook pre-trained weights. So that is very good, right? This is, this is basically as good as it could get because Facebook has all these GPUs and they can train a model as big as they want. I was able to reach a 1.34 using my pre-trained weights. So this is a reasonable start, especially when you can compare it to the randomized weights. So this was a backbone that wasn't pre-trained with the masked language modeling strategy. I just trained a full BERT model on my data, on the squad data, and kind of produce this, right? 4.31. So we're seeing some evidence there. And more specifically, the Facebook model gets almost 90% F1 score on the squad data set, where my model gets close to 75, 76%, which is good, right? Pretty good, pretty close. And we get 5% on the randomized. So this is garbage. So we're seeing clear evidence that this pre-training strategy learned something about language that's interesting enough for it to be able to do this squad task. Now, if we take a quick look at the RoBERTa paper, RoBERTa, right? If we take a quick look at this, we can see that it was trained on quite a bit of data. So it was trained on the book corpus, which we did, I guess it doesn't have Wikipedia. I don't remember then. Okay, so it was trained on book corpus, CC News, open web text, and stories, right? So this is quite a bit of data, over 160 gigabytes of uncompressed text. So definitely more than what I trained it on. And resources wise, it was also trained on just more GPUs, right? More GPUs. But all the code we wrote is basically identical to what we can expect to get, right? So all the code we wrote would have worked even better. So here we go, books and wiki. It would have worked even better if we had more GPUs, could do larger batches, that sort of stuff. The things that typically help these models. You can also say they trained it for significantly longer, right? They trained for 500K steps just because they have the resources for that. Either way, I will call that here. Again, as a recap, what you should have gotten here is basically a code base that could potentially reproduce the entire RoBERTa architecture, which is awesome. We were able to prepare a sizable data set. We're able to write the entire, basically rewrite the masking strategy to do batches rather than single samples at a time. We wrote a entire model. We rewrote the entire model. It's basically the same as what we had done earlier in the kind of the primer to this video, just with a little bit more modularity, and a little bit more control over some of the things that we care about. We also included this, weight initialization strategy, that sort of stuff. And we were able to write a full pre-training script that will do distributed training, mixed precision training, all of the stuff that we love about training neural networks. In the next video, we will be implementing the RoBERTa for question answering, so what I had mentioned. And so I will see you in the next one.